A cosmic void is one of the largest structures in the universe, not because of what it contains, but because of what it lacks. These are vast regions of space, often hundreds of millions of light years across, where galaxies, gas and dark matter are remarkably scarce. While galaxy clusters form the dense nodes of the cosmic web, voids are its empty threads, making up most of the universe's actual volume. For decades, astronomers assumed our galaxy occupied a fairly typical region of space, surrounded by an average distribution of matter. But new observations suggest otherwise. The Milky Way may sit inside a local underdense region, a cosmic void, large enough to subtly influence how we measure the universe itself. The empty heart of everything. Imagine standing in the middle of an ocean so vast that you cannot see land in any direction. Now imagine that the ocean is not water, but emptiness. Pure, dark, cosmic emptiness stretching for hundreds of millions of light years. This is where we live. Not on the edge of this void, not near its boundary, but deep inside it, floating in one of the most desolate regions of the observable universe. We are inside one of these voids. Our Milky Way galaxy sits in an enormous bubble of emptiness called the KBC void, stretching roughly 2 billion light-years across, one of the largest known voids in the observable universe. In 1929, Edwin Hubble made a discovery that changed everything. By measuring the light from distant galaxies, he found that they were all moving away from us, and the farther away they were, the faster they receded. This wasn't because we occupied some special central position. It was because space itself was expanding, carrying galaxies apart like dots on an inflating balloon. The universe had a history. It was born in a hot, dense state we now call the Big Bang, and it's been expanding and cooling ever since. For decades after Hubble's discovery, astronomers assumed that while the universe was expanding, matter was distributed more or less uniformly throughout space. Sure, galaxies clustered together in groups and larger congregations, but on average, if you picked any random cubic billion light-years of space, it should contain roughly the same amount of matter as any other such volume. This assumption, called the cosmological principle, held that the universe was homogeneous and isotropic on large scales, the same everywhere and in all directions. The first hints that something was wrong came in the 1970s and 1980s, when astronomers began systematically measuring distances to thousands of galaxies. The technique was straightforward. Measure a galaxy's redshift, how much its light has been stretched toward redder wavelengths by cosmic expansion, and use that to calculate its distance. Plot enough galaxies in 3 dimensions, and you'd see how matter was distributed through space. What they saw shocked everyone. Galaxies weren't scattered randomly or uniformly. Instead, they traced out a pattern that looked organic, almost biological. There were dense filaments of galaxies stretching across hundreds of millions of light years. There were flat sheets or walls where galaxies congregated in 2-dimensional surfaces. At the intersections of filaments sat massive clusters containing thousands of galaxies. And between all these dense structures were enormous regions that contained almost nothing, the cosmic voids. The first major void was discovered in 1981 by astronomer Robert Kirshner and his colleagues. They were surveying galaxies in the constellation Bootes when they found a region about 330 million light-years across that contained almost no galaxies. In a volume where they expected to find about 2,000 galaxies based on the cosmic average, they found only 60. The Bootes void, as it came to be called, was so empty and unexpected that astronomers initially struggled to believe it was real. They checked their instruments, recalibrated their measurements, and looked for errors in their data. But the void remained. It was real, vast, and virtually empty. More surveys followed, each revealing more voids. The Cepheid Redshift Survey in the 1980s mapped tens of thousands of galaxies and revealed what came to be called the Stick Man, a pattern of filaments and voids that looked like a cosmic stick figure sketched across hundreds of millions of light years. The 2-degree field galaxy redshift survey and the Sloan Digital Sky survey in the 1990s and 2000s mapped millions of galaxies, revealing the cosmic web in stunning 3-dimensional detail. Everywhere astronomers looked, they found the same pattern: dense filaments and walls surrounding vast empty voids. The voids weren't just small gaps between galaxy clusters. They were enormous, some spanning 500 million light-years or more. They occupied roughly 80% of the universe's total volume, even though they contained less than 10% of its matter. The universe wasn't a uniform distribution of galaxies, but a foam-like structure, with matter concentrated in thin walls surrounding enormous bubbles of emptiness. The physics behind void formation became clear as astronomers developed better models of cosmic evolution. In the very early universe, tiny quantum fluctuations during the inflationary epoch created regions that were slightly denser or less dense than average, variations of only about 1 part in 100,000. Over billions of years, gravity amplified these tiny differences. Denser regions attracted more matter, becoming denser still in a runaway process. Underdense regions lost matter to their surroundings, becoming progressively emptier. The small fluctuations grew into the massive structures we see today. Dark matter played a crucial role. This mysterious substance, which makes up about 85% of all matter but interacts only through gravity, began collapsing into structures earlier than normal matter. It created a gravitational scaffolding, a framework of dark matter halos and filaments into which normal matter would later fall. The cosmic web we observe in galaxy surveys is actually just the visible tip of a much larger dark matter web that pervades all of space. Then came dark energy. In 1998, 2 teams of astronomers studying distant supernovae made an astonishing discovery. The universe's expansion wasn't slowing down as everyone expected, it was speeding up. Some mysterious force, which scientists called dark energy, was pushing space apart at an accelerating rate. This force makes up about 68% of the total energy content of the universe, and it has profound effects on cosmic structure, especially on voids. In dense regions like galaxy clusters, gravity is strong enough to overcome dark energy's push. Clusters remain gravitationally bound despite cosmic expansion. But in voids, where matter density is far below average, dark energy dominates completely. Voids don't just exist passively, they actively expand, pushing matter toward their edges and growing larger over time. Dark energy turns voids into cosmic vacuum cleaners, evacuating matter and creating ever larger regions of emptiness. By the early 2000s, astronomers had catalogued thousands of voids across billions of light years. They measured their sizes, shapes, and densities. They studied the few galaxies that did exist within voids and found them to be different from galaxies in denser regions, smaller, bluer, more actively forming stars, and more isolated. They tracked how voids grew over cosmic time by comparing nearby voids to distant ones, seeing the universe at earlier stages of evolution. And then came a disturbing realization. When astronomers looked at the galaxy distribution in our own cosmic neighborhood, within about 1 billion light-years of the Milky Way, they noticed something odd. The density of galaxies seemed lower than the cosmic average. Not dramatically lower, but measurably so. Our local universe appeared to be underdense by about 20 to 30%, compared to what large-scale surveys showed for the universe as a whole. At first, this was dismissed as a statistical fluctuation or observational bias. Maybe we just hadn't surveyed our local volume completely enough. Maybe faint galaxies were being missed. But as more data accumulated through the 2000s and 2010s, the underdensity persisted. Multiple independent studies using different techniques and datasets reached the same conclusion. Our local universe is less dense than average. We live in a region where matter is scarce. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie published a detailed analysis showing that our local region is consistent with being inside a large cosmic void. They estimated the void extended roughly 1 to 2 billion light-years in diameter, with us located not on its edge but relatively close to its center. This would make it one of the largest voids known in the entire observable universe. They named it the KBC void after their initials. The discovery was controversial. Some astronomers questioned the statistical significance or argued about where exactly to draw the void's boundaries. Voids don't have sharp edges. They transition gradually from underdense to normal density, so defining their precise extent is somewhat subjective. Different studies using different methods obtained different values for the KBC void's size and depth. But the basic conclusion remained: we live in an underdense region, and that region is large enough to qualify as a major cosmic void. This realization has profound implications. Every measurement we make of the universe is potentially biased by our location. When we measure how fast the universe is expanding using nearby supernovae, we're measuring expansion in an underdense region where the local rate might be higher than the cosmic average. When we count galaxies and measure structure, we're doing so from inside a void, which may skew our perceptions. When we try to understand the fundamental laws of cosmology, we must account for the fact that we're not observing from a typical location, but from one of the universe's emptiest regions. The KBC void affects not just our observations, but our cosmic address. We are void dwellers. The Milky Way, our local group of galaxies, and everything we can see within hundreds of millions of light-years exists inside this enormous bubble of underdensity. The nearest rich galaxy clusters, the Virgo cluster, the Coma cluster, sit at or beyond the void's edges. We are not in the cosmic mainstream, but in the quiet outskirts, observers from the periphery trying to understand the whole. What is a cosmic void? To understand what we're living inside, we first need to understand what a cosmic void actually is. The term sounds simple enough, an empty region of space, but the reality is far stranger and more specific. Cosmic voids are not just random patches where galaxies happen to be absent. They are fundamental structures of the universe, carved out by cosmic expansion and dark energy, shaped by gravity and time into the largest coherent structures known to exist. A cosmic void is a region of space with significantly lower galaxy density than the cosmic average. Imagine the universe as a three-dimensional network where galaxies cluster along filaments and sheets, like cities connected by highways. The voids are the spaces between these highways, vast rural expanses where very little exists. The typical void contains less than 10% of the average cosmic density, and some contain even less. They are underdense regions where dark matter is scarce. Baryonic matter, the normal matter that makes up stars and gas, is even scarcer, and galaxies are rare or entirely absent. The sizes of these voids are almost incomprehensible. Small voids might span 30 to 50 million light-years, which is already larger than the distance between our Milky Way and most nearby galaxy clusters. Medium voids range from 100 to 150 million light-years. Large voids can exceed 300 million light-years. And supervoids, the giants of the cosmic landscape, stretch beyond 500 million light-years. To put this in perspective, light traveling at 186,000 miles per second would take 500 million years to cross the largest voids. The entire observable universe is only about 93 billion light-years across, meaning the largest voids occupy a substantial fraction of cosmic volume. These voids are not perfectly empty. Within even the most desolate voids, you'll find a handful of dwarf galaxies, scattered like remote cabins in a wilderness. These void galaxies are different from their cousins in denser regions. They tend to be smaller, bluer, and more actively forming stars. They rotate more slowly and have less heavy elements in their gas. Living in such isolation shapes them differently, without nearby galaxies to interact with. They evolve in peaceful solitude, forming stars at their own pace, without the violent mergers and tidal disruptions that affect galaxies in clusters. The boundaries of voids are not sharp walls, but gradual transitions. As you move from the void's center toward its edge, galaxy density increases slowly at first, then more rapidly until you reach the void's wall, the shell of matter that surrounds the empty region. These walls are not physical barriers, but concentrations of galaxies and dark matter that mark the transition from underdense to overdense regions. The walls themselves are often quite thin compared to the void's diameter, typically only 20 to 30 million light-years thick. Beyond the walls lie filaments, dense streams of galaxies stretching across the cosmos, and at the intersections of filaments you find galaxy clusters, the densest environments in the universe. The shape of voids varies considerably. Some are roughly spherical, like soap bubbles. Others are elongated, stretched like cosmic cigars. Many are irregular, with protrusions and indentations that give them a lumpy appearance. This variety reflects the complex gravitational history of each void, shaped by the distribution of matter around it and the specific conditions in the early universe from which it grew. Voids are constantly evolving. They expand over time, pushing matter outward and growing larger as the universe itself expands. This expansion is driven by dark energy, the mysterious force that causes the universe's expansion to accelerate. Inside voids, where matter density is low, dark energy dominates even more than in denser regions. This means voids expand faster than the universe's average expansion rate, actively pushing galaxies toward their edges and evacuating matter from their interiors. The number of voids in the observable universe is staggering. Current surveys have catalogued tens of thousands of voids, and the total number is likely in the hundreds of thousands or millions. They occupy approximately 80 to 90% of the universe's volume, even though they contain only a tiny fraction of its matter. This is one of the most counterintuitive facts about cosmic structure. Most of the universe is empty space, and that empty space is organized into distinct structural elements. Astronomers classify voids by several different schemes. Some use size as the primary criterion, creating categories like mini-voids, voids, and supervoids. Others classify by galaxy density, distinguishing between nearly empty voids and those with sparse populations. Still others focus on shape, separating spherical voids from elongated or irregular ones. There's also a distinction based on location. Voids can exist in isolation, surrounded by filaments on all sides, or they can connect to other voids, forming vast networks of empty space. The existence of cosmic voids tells us something profound about the early universe. When the cosmos was only 380,000 years old, it was filled with tiny density fluctuations, regions where matter was slightly more or less concentrated than average. Over billions of years, gravity amplified these fluctuations. Denser regions attracted more matter and grew denser still, eventually becoming galaxy clusters and filaments. Underdense regions lost matter to their surroundings and became voids. The cosmic web we see today is the gravitational echo of those primordial fluctuations, stretched and amplified by 13.8 billion years of cosmic evolution. Understanding voids requires understanding the cosmic web itself, the largest scale structure in the universe. The web consists of 4 components: clusters, dense nodes where many galaxies congregate; filaments, streams of galaxies connecting clusters; walls, sheet-like structures of galaxies; and voids, the empty regions surrounded by these denser features. These components are not separate entities but parts of a single interconnected structure. Matter flows from voids to walls, from walls to filaments, and from filaments to clusters, following the gravitational pull of dark matter. The physics governing voids is surprisingly complex. Gravity wants to pull matter into voids, filling them in. Dark energy wants to push matter out, emptying them further. The balance between these forces determines how voids evolve. In the early universe, when matter density was higher, gravity was stronger and voids expanded slowly. As the universe aged and dark energy became more dominant, void expansion accelerated. Today, voids are growing faster than ever, and this growth will continue indefinitely as dark energy pushes the universe toward an ever more empty, dispersed state. Scientists study voids using several techniques. galaxy redshift surveys map the three-dimensional positions of millions of galaxies, revealing the cosmic web and identifying void regions. Gravitational lensing can detect voids by their effect on light from more distant objects. Light traveling through a void is bent differently than light passing through denser regions. The cosmic microwave background shows imprints of supervoids as cold spots, regions where photons lose energy climbing out of the void's gravitational well. Each technique adds another layer to our understanding. The theoretical framework for voids comes from cosmological simulations. Astronomers use supercomputers to simulate the evolution of the universe from the Big Bang to today, tracking how dark matter and normal matter interact under gravity's influence. These simulations successfully reproduce the cosmic web, including its voids, with remarkable accuracy. They show that voids are inevitable consequences of gravitational collapse in an expanding universe. Wherever you start with tiny density fluctuations and let gravity act for billions of years, voids will emerge. Cosmic voids challenge our intuition about emptiness. We think of empty space as passive, as nothing. But voids are active structures with their own dynamics. They push matter, affect cosmic expansion, and shape the evolution of galaxies. They are as much a part of the universe's architecture as galaxies and clusters, perhaps more fundamental because they occupy most of the volume. To understand the cosmos, we must understand its emptiness as much as its fullness. And now we must face the unsettling reality. We live inside that emptiness, making it our cosmic home. The Great Surveys and the Emergence of Cosmic Structure. The discovery of cosmic voids was not instantaneous. It emerged slowly from decades of painstaking work by astronomers who mapped the universe one galaxy at a time. Before the 1970s, astronomers knew galaxies existed in clusters, but they had no clear picture of large-scale structure. The universe might have been uniform on average, with galaxies scattered randomly, but clustering together occasionally by chance. Or it might have deeper organization. The only way to find out was to map the positions of galaxies in 3 dimensions, not just their locations on the sky, but their distances from Earth. The challenge was measuring distance. Stars and galaxies don't come with distance markers. You can see them on the sky, but determining whether a galaxy is near or far requires indirect methods. The breakthrough came from understanding redshift. When a galaxy moves away from us, the wavelengths of light it emits stretch out, shifting toward the red end of the spectrum. The faster the galaxy recedes, the greater the redshift. And because the universe is expanding, distant galaxies recede faster than nearby ones, a relationship called Hubble's law. By measuring a galaxy's redshift, astronomers could estimate its distance. This simple principle opened the door to 3-dimensional cosmic cartography. In the late 1970s and early 1980s, several pioneering galaxy surveys began the work of mapping cosmic structure. The CFA Redshift Survey, led by Mark Davis, John Huchra, Dave Latham, and John Tonry at the Harvard-Smithsonian Center for Astrophysics, measured redshifts for thousands of galaxies. When they plotted the results in 1986, they revealed something no one expected, a pattern that looked like a stick figure drawn in galaxies. This became known as the CFA Stickman, or the Great Wall and Stickman, and it showed that galaxies were not scattered randomly. They lined up in filaments and sheets with large empty regions between them. The stick figure was crude. The survey covered only a small slice of sky, but it hinted at vast structure. Galaxies congregated in thin sheets and filaments, avoiding certain regions entirely. The empty regions, which would soon be called voids, were enormous. The largest void in that early survey spanned about 150 million light-years. For the first time, astronomers saw direct evidence that the universe had a foam-like or sponge-like structure on the largest scales. The discovery electrified the astronomical community. Theorists had predicted that the universe should show structure on large scales due to gravitational collapse. but seeing it confirmed was different. The voids were particularly intriguing because they were so empty. It wasn't just that galaxies were sparse in these regions, they were virtually absent. The contrast between dense filaments and empty voids was stark and demanded explanation. Through the 1980s and 1990s, survey technology improved dramatically. Astronomers developed multi-fiber spectrographs that could measure redshifts for hundreds of galaxies simultaneously. Telescopes became larger and more sensitive. Computer technology advanced, allowing researchers to process and visualize vast datasets. Each new survey went deeper and wider, revealing more of the cosmic web. The Las Campanas redshift survey in the 1990s mapped over 26,000 galaxies and revealed the three-dimensional structure in unprecedented detail. The voids showed up clearly as vast underdense regions surrounded by sheets and filaments of galaxies. The survey confirmed that voids occupied most of the universe's volume. It also showed that voids came in different sizes and shapes, some nearly spherical, others elongated or irregular. Then came the Sloan Digital Sky Survey, SDSS, which began observations in 2000 and continues in various forms today. SDSS revolutionized our understanding of cosmic structure by measuring redshifts for millions of galaxies. The three-dimensional maps it produced showed the cosmic web in stunning clarity. Filaments stretched across hundreds of millions of light-years. Sheets of galaxies formed walls between voids, and the voids themselves appeared as vast empty bubbles, some so large they challenged theoretical models of structure formation. One particular feature discovered by SDSS and related surveys was the Sloan Great Wall, a vast structure of galaxies spanning over 1.4 billion light-years. But equally important were the voids surrounding such structures. Astronomers catalogued void after void, measuring their sizes, shapes, and galaxy populations. Some voids were truly empty, containing only a handful of faint dwarf galaxies. Others had sparse populations of small galaxies scattered through their volumes. The 2-degree field galaxy redshift survey, conducted in parallel with SDSS using telescopes in Australia, mapped the southern sky and confirmed the same pattern: filaments, walls, clusters, and voids organized into a cosmic web. The agreement between surveys removed any doubt. This was the true large-scale structure of the universe. As surveys grew larger, they revealed something else. Our local region of the universe, within about 1 billion light-years of the Milky Way, seemed different from more distant regions. The average density of galaxies appeared lower. The distribution of matter seemed underpopulated. At first, astronomers attributed this to selection effects or statistical fluctuations. After all, the universe should be the same on average everywhere. This is the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. But the evidence kept mounting. Studies of galaxy luminosity functions, the distribution of galaxy brightnesses, showed that nearby galaxies were slightly dimmer on average than expected. Studies of galaxy clustering found that local structure was less pronounced than predictions suggested. Measurements of the local expansion rate using nearby supernovae gave results that didn't quite match the expansion rate measured from the cosmic microwave background, which samples the entire observable universe. These discrepancies were small, just a few percent here and there, but they were persistent. Some astronomers began to suspect that we lived in an unusual part of the universe, specifically in a region where matter density was below average. The idea was controversial. It seemed to violate the cosmological principle. It suggested that our perspective on the universe might be biased by our location, and it meant that all our measurements of cosmic parameters might need correction. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie published a paper that brought these concerns into focus. They analyzed galaxy surveys and showed that our local region was consistent with being inside a large cosmic void extending roughly 1 billion light-years in all directions. The void wasn't perfectly spherical, it was somewhat flattened and irregular. but its existence seemed clear. They calculated that we were near the center of this void, not on its edge. The discovery was not universally accepted at first. Other astronomers questioned the statistical significance of the result. They pointed out that cosmic structure is irregular, and you can always find regions that look underdense if you choose your boundaries carefully. The debate continued through the mid-2010s, with different groups analyzing data in different ways and reaching different conclusions. But as more data accumulated, the evidence became harder to dismiss. The KBC void, as it came to be called, showed up in multiple independent analyses. Its properties were measured with increasing precision. Its size was estimated at 1.5 to 2 billion light-years in diameter, making it one of the largest voids known. And our position within it, not on the edge but toward the center, meant that all our observations of the distant universe were filtered through this underdense region. The surveys that revealed cosmic voids also showed that such voids are common. The universe is riddled with them. They come in all sizes, from small voids a few tens of millions of light-years across to supervoids spanning billions. They are not exotic structures, but fundamental features of cosmic architecture. If voids are common, it's not surprising that we might find ourselves in one. In fact, given that voids occupy most of the universe's volume, it would be more surprising if we weren't in a void. The maps produced by Galaxy surveys are among the most important scientific achievements of the past 50 years. They show the universe not as a uniform scattering of galaxies, but as an intricate web of structure shaped by gravity, dark matter, and dark energy. The voids are as much a part of this structure as the filaments and clusters. They are not background features, but foreground. They define the architecture of the cosmos. And now we know that we inhabit one of these defining features, living our entire existence inside a cosmic void that shapes everything we observe. The KBC void, our cosmic neighborhood. The KBC void is not just any void, it is our void, the cosmic structure that defines our local universe and influences every astronomical observation we make. Understanding this void, its size, shape, density, and evolution, is essential to understanding our place in the cosmos and correcting for the biases it introduces into our measurements. The void extends roughly 1.5 to 2 billion light-years in diameter, though its exact boundaries are fuzzy and somewhat subjective. Like all voids, it doesn't have sharp edges, but gradual transitions from underdense to normal and then overdense regions. At its center, where we are located, the matter density is approximately 20 to 30% below the cosmic average. This might not sound like much, but in cosmic terms, it's significant. It means there are fewer galaxies, less dark matter, and less gravitational pull in our neighborhood than in typical regions of the universe. Our position within the KBC void is particularly important. We're not on the edge looking out, but close to the center, surrounded by emptiness in all directions. The Milky Way sits roughly 400 to 500 million light-years from the void's center, which places us well within its interior. The local group of galaxies, including Andromeda, the Triangulum galaxy, and dozens of smaller galaxies, occupies a similar position. We're all floating together in this underdense region. The shape of the KBC void is not a perfect sphere. Detailed analyses show it somewhat elongated and flattened, with its long axis extending farther than its short axis. This asymmetry reflects the complex gravitational environment that formed it. Nearby massive structures, like the Virgo supercluster to our north, have pulled matter away from some directions more than others, stretching the void into an irregular shape. The void's density profile, how matter distribution changes from its center to its edge, has been measured using galaxy surveys. At the very center, the galaxy density is about 70% of the cosmic average. Moving outward, the density rises gradually, reaching the cosmic average at about 700 to 800 million light-years from the center. Beyond this radius, density continues to rise as you enter the void's walls and the denser filaments beyond. The gradient is smooth, not stepped, reflecting the continuous nature of cosmic structure. Inside the KBC void, galaxies are not just fewer, they're different. Studies of void galaxies within our local volume show they tend to be smaller and bluer than galaxies in denser regions. They have more active star formation relative to their stellar mass. They contain more gas and fewer heavy elements. These properties reflect the peaceful environment of voids. Without frequent interactions and mergers, void galaxies evolve more slowly, retaining their gas and forming stars at steady rates over billions of years. The void's expansion rate is another crucial property. Because matter density is lower inside voids, the local expansion rate of space should be slightly higher than the cosmic average. This is exactly what some measurements suggest. When astronomers use nearby supernovae to measure the Hubble constant, the rate at which the universe is expanding, they get a value of about 73 kilometers per second per megaparsec. But when they calculate the Hubble constant from the cosmic microwave background, which samples the whole universe, they get about 67 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, has puzzled cosmologists for years. Living in a void could explain at least part of this difference, though the debate continues. The gravitational influence of the KBC void extends beyond its boundaries. The void acts like a gravitational bubble, pushing outward on surrounding matter. This creates a coherent bulk flow, a large-scale motion of galaxies, directed away from the void's center. Our local group is participating in this flow, moving at several hundred kilometers per second relative to the cosmic microwave background. Part of this motion is due to nearby attractors like the Virgo cluster and the Great Attractor, but part may be the void pushing us outward. The history of the KBC void stretches back billions of years. In the early universe, the region that would become our void was slightly less dense than average, perhaps only a few percent less. Over time, gravity amplified this small difference. Matter on the edges of the underdense region felt stronger gravitational pull from denser regions outside and began flowing outward. Meanwhile, the underdense region itself had less gravity to hold matter in place, allowing it to be pulled away more easily. Slowly, over billions of years, the void grew and deepened. By the time the universe was a few billion years old, the KBC void was already recognizable as a distinct underdense region. Galaxies that formed within it were isolated, with large distances separating them from neighbors. The local group formed in this environment, in a relatively quiet corner of the universe where major mergers and interactions were rare. This peaceful setting may have been crucial for the development of complex life on Earth. Had we formed in a dense cluster environment, frequent encounters with other galaxies might have disrupted the Milky Way and prevented the stable conditions needed for life. Today, the KBC void continues to evolve. It's expanding faster than the cosmic average, driven by dark energy's influence. The acceleration of cosmic expansion means that voids are winning their battle against gravity. They're growing larger and more empty, pushing matter ever farther towards their edges. In the far future, as dark energy continues to dominate, the KBC void will grow even larger. Galaxies at its edges will accelerate away, eventually moving beyond our cosmic horizon. Our local universe will become progressively more isolated. The discovery of the KBC void has important implications for cosmology. Many fundamental cosmic parameters, the Hubble constant, the matter density parameter, the dark energy equation of state, are measured using observations of our local universe. If our local universe is inside a void, these measurements may be biased. We might be measuring a local value that differs from the true cosmic average. This possibility has spawned a subfield of cosmology focused on correcting for local underdensity and understanding how much it affects our measurements. Some cosmologists have proposed using the void to explain cosmological anomalies. The Hubble tension, for example, might be resolved if we account for our location in an underdense region. The discrepancy between different measurements of the matter density parameter might similarly reflect local bias. However, these explanations are controversial. Most studies suggest that while the void does introduce some bias, it's not large enough to fully explain the Hubble tension or other major cosmological problems. The debate continues. The KBC void also affects how we interpret observations of distant objects. Light from distant galaxies travels through the void on its way to us, and this journey affects the light in subtle ways. Gravitational lensing by matter along the line of sight is weaker when the light passes through a void, making distant objects appear slightly fainter than they would otherwise. The integrated Sachs-Wolf effect, which causes photons to gain or lose energy as they pass through changing gravitational potentials, creates a signal in the cosmic microwave background that depends on the voids and overdensities along the line of sight. All these effects must be carefully accounted for when analyzing distant observations. Understanding the KBC void requires combining data from multiple sources. Galaxy surveys map the distribution of galaxies in 3 dimensions. Gravitational lensing studies measure the distribution of dark matter. Measurements of galaxy. Peculiar velocities, their motions relative to the cosmic expansion, trace the gravitational field and reveal mass concentrations and deficits. The cosmic microwave background provides an independent measure of structure along the line of sight to the early universe. By combining all these probes, astronomers build a comprehensive picture of the void's properties. The name KBC void honors the astronomers who first characterized it in detail, but the structure was hinted at in earlier studies. In the 1980s and 1990s, several papers noted that the local universe seemed underdense. The term local void appeared occasionally in the literature, but it wasn't until the 2013 paper by Keenan, Barger and Cowie that the evidence was compiled convincingly and the void's parameters were quantified. Since then, numerous studies have refined these measurements, confirming the void's existence and properties. Our residence in the KBC void is not unique. Many galaxies live in voids, perhaps 10 to 15% of all galaxies. What makes our situation special is the void's large size and the fact that we're near its center rather than its edge. Most void galaxies live in smaller voids or near void boundaries. To live in a supervoid center is relatively rare, though not impossibly so. It's estimated that perhaps 1% of galaxies occupy such positions. So while we're not typical, we're not impossibly special either. The KBC void is our cosmic home. It defines our local environment, shapes the galaxy distribution we observe, affects our motion through space, and biases our measurements of cosmic parameters. It is as fundamental to our cosmic address as our location in the Milky Way or our position in the solar system. We are void dwellers, and understanding this changes how we interpret the universe around us. How cosmic voids form and evolve. To understand how we ended up inside a cosmic void, we need to understand how voids form in the first place. The story begins in the very early universe, mere moments after the Big Bang, when quantum fluctuations created tiny variations in density, seeds that would eventually grow into all cosmic structure. When the universe was only a fraction of a second old, it underwent a period of rapid expansion called inflation. During this brief moment, the universe expanded exponentially, stretching quantum fluctuations to cosmic scales. These fluctuations were incredibly small variations in density of only 1 part in 100,000, but they were real, and they were everywhere. Some regions were slightly denser than average, containing a bit more energy and matter. Other regions were slightly less dense. These tiny differences were frozen into the fabric of space-time and would become the blueprint for everything that came after. As the universe continued to expand and cool, these density fluctuations began to grow under the influence of gravity. This process is called gravitational instability, and it's the fundamental mechanism that builds cosmic structure. In regions where density was slightly higher than average, the extra matter created slightly stronger gravity, which attracted even more matter from the surroundings. This made the region denser still, increasing its gravity further, which attracted more matter, a runaway feedback process. Over millions and billions of years, these overdense regions collapsed into galaxy clusters, galaxies, and eventually stars and planets. But what happened in the underdense regions? They experienced the opposite process. With less matter, they had weaker gravity and couldn't hold on to the material within them as effectively. Matter felt stronger gravitational pull from neighboring overdense regions and began flowing outward toward the denser areas. As matter left the underdense region, gravity there became even weaker, making it easier for more matter to escape. These regions became voids, evacuated zones where matter density fell below the cosmic average. This process didn't happen instantaneously. In the early universe, when matter density was high everywhere and gravity was strong, the underdense regions couldn't empty out very much. They remained only slightly less dense than average. But as the universe expanded and overall density decreased, gravity's grip weakened. The underdense regions could evacuate more effectively. By the time the universe was a few billion years old, recognizable voids had formed, regions where galaxy density was noticeably lower than average. Dark matter played a crucial role in this process. Dark matter makes up about 85% of all matter in the universe, and it feels only gravity. It doesn't interact with light or normal matter except through gravitational attraction. In the early universe, dark matter began collapsing into structures before normal matter could. It formed the gravitational scaffolding, dark matter halos, into which normal matter would later fall. The distribution of dark matter determined where galaxies would form and where voids would appear. Computer simulations of cosmic structure formation, which track the evolution of dark matter under gravity, successfully reproduce the void structure we observe. These simulations start with initial conditions matching the density fluctuations measured in the cosmic microwave background. They then let gravity act for billions of years, watching as structure grows. The results are striking. The simulations naturally produce a cosmic web of filaments, walls, clusters, and voids that closely matches what we see in galaxy surveys. The voids arise inevitably from gravitational dynamics. They are not special conditions but natural outcomes of structure formation. The shape of voids depends on the initial distribution of matter and the gravitational influence of surrounding structures. A void that forms in a region surrounded by uniform density on all sides will tend to be spherical. Matter flows outward equally in all directions. But most voids don't form in such perfect conditions. Nearby overdensities pull matter preferentially in certain directions, elongating the void or creating irregular shapes. The voids we observe are rarely perfect spheres. Most are somewhat elongated or lumpy, reflecting the asymmetric gravitational environment in which they formed. As voids grow, they affect their surroundings. Matter flowing out of voids piles up at the edges, creating shells of enhanced density around the void. These shells are the void walls visible in galaxy surveys, the boundaries between underdense void interiors and the filaments beyond. The walls are not static. They grow as more matter accumulates. Eventually, if two voids are adjacent, their walls can merge, creating larger voids from smaller ones. This hierarchical merging process means voids grow over time, with small voids combining into larger ones. Dark energy dramatically changed void evolution. Before the universe was about 5 billion years old, matter density was high enough that gravity dominated cosmic dynamics. Voids grew slowly during this era, limited by gravity's pull. But as the universe expanded, matter density decreased, while dark energy density remained constant, or nearly so. Eventually, around 5 billion years after the Big Bang, dark energy began to dominate. This caused the universe's expansion to accelerate rather than decelerate. The effect on voids was profound. Dark energy acts as a kind of anti-gravity, pushing space apart rather than pulling it together. In dense regions like galaxy clusters, gravity is strong enough to overcome dark energy's push, holding structures together. But in voids, where matter density is low and gravity is weak, dark energy dominates completely. Voids began expanding faster, actively pushing matter toward their edges. The evacuation of voids accelerated. Today, voids are growing rapidly, and this growth will continue indefinitely as dark energy maintains its dominance. The expansion of voids is not just passive growth, it's an active process. The void's low density creates a gravitational potential well that is shallower than surrounding regions. As photons from the cosmic microwave background pass through a void, they climb out of this shallow well and gain energy. This creates a slight temperature increase in the microwave background called the integrated Sachs-Wolf effect. By measuring this effect, astronomers can detect and study voids independently of galaxy surveys. The rate at which voids expand depends on several factors. Larger voids expand faster than smaller ones because they have more space over which dark energy can act. Voids in regions with lower overall density expand faster than those in denser environments. The specific properties of dark energy, its equation of state, and how it evolves over time also affect void expansion. By measuring void expansion rates, astronomers can constrain dark energy's properties, making voids valuable probes of fundamental physics. Not all voids evolve the same way. Small voids in dense environments may stop growing or even collapse as surrounding structures pull matter back inward. Large voids in typical environments continue growing indefinitely. Supervoids like the KBC void represent the extreme case. They're large enough and old enough that they've evacuated most of their matter and will continue expanding for the rest of cosmic time. The galaxies that do exist inside voids have interesting evolutionary histories. In the early universe, before voids were well developed, these regions contained more matter. Some of that matter collapsed into galaxies before it could flow out of the void. These galaxies found themselves increasingly isolated as the void around them emptied out. Other void galaxies formed from small pockets of slightly overdense material within the void, tiny islands of structure in an ocean of emptiness. These formation scenarios produce different types of galaxies with different properties, which astronomers can use to reconstruct void history. Void galaxies evolve differently from their counterparts in dense environments. In galaxy clusters, frequent interactions and mergers transform spiral galaxies into elliptical ones, stripping away gas and shutting down star formation. This environmental processing is much weaker in voids. Void galaxies interact rarely, maintain their gas reserves, and continue forming stars for billions of years longer than cluster galaxies. They represent cosmic time capsules, preserving conditions that were more common in the early universe. The formation of the KBC void followed these general principles, but with specific details unique to our region. About 10 to 12 billion years ago, the region that would become our void was slightly underdense, perhaps 5% below the cosmic average. This was enough. Matter began flowing outward, pulled by denser structures forming outside our region. The Virgo supercluster, the Coma cluster, and other large structures were growing to our north and east, their gravity pulling matter toward them and away from what would become our void. Over billions of years, the void deepened and expanded. By the time the universe was 7 or 8 billion years old, our region was recognizably underdense, with fewer galaxies and less dark matter than average. The Milky Way and local group formed in this environment, in a relatively quiet region where major interactions were rare. As dark energy began dominating the universe's dynamics around 5 billion years ago, void growth accelerated. Our void is still growing today, pushing the nearest rich structures farther away as space expands. Understanding void formation and evolution is crucial for cosmology. Voids are sensitive probes of gravitational physics, dark matter properties, and dark energy dynamics. They also serve as laboratories for studying galaxy evolution in extreme environments. The fact that we live inside one gives us a unique perspective. We can study void physics from within, observing the detailed properties that would be difficult to measure from outside. The cosmic web, filaments, walls, clusters, and voids. To truly understand cosmic voids, we must see them in their proper context as parts of the cosmic web, the largest structure in the universe. The cosmic web is not a metaphor or an artistic interpretation. It's a real physical structure, traced by billions of galaxies, arranged in a pattern that resembles a three-dimensional spider web stretching across the entire observable universe. The cosmic web consists of four basic components, each playing a distinct role in cosmic architecture. At the nodes where multiple filaments intersect sit galaxy clusters, the densest environments in the universe where hundreds or thousands of galaxies congregate. These clusters are gravity wells so deep that they trap hot gas reaching tens of millions of degrees, visible in X-ray observations as vast clouds surrounding the galaxies. The Coma cluster, the Virgo cluster, and the Perseus cluster are examples visible from our location inside the KBC void. Connecting the clusters are filaments, long streams of galaxies and dark matter stretching across hundreds of millions of light years. Filaments are the highways of the cosmic web, channels along which matter flows from voids toward clusters. They contain most of the galaxies in the universe. Roughly 60% of all galaxies live in filaments. These structures are not uniform. They're denser at their centers and fade toward their edges. They can be thin, only a few million light-years across, or thick, spanning tens of millions. Some filaments extend for over 1 billion light-years, connecting distant clusters in an unbroken chain. Where filaments meet at shallow angles rather than points, they create walls or sheets, two-dimensional surfaces of galaxies. The Great Wall discovered in early galaxy surveys is an example, a vast sheet of galaxies stretching over 500 million light-years. Walls are thinner than filaments, typically only 5 to 10 million light-years thick, but they can extend for enormous distances in the other two dimensions. They mark the boundaries between adjacent voids, separating one empty region from another. And then there are the voids, the vast empty regions surrounded by walls and threaded by occasional filaments. The voids are not simply the absence of structure. They are structural elements in their own right. They occupy most of the universe's volume, typically 80 to 90%, though they contain only 10 to 20% of its matter. The voids define the cosmic web as much as the filaments and clusters do. You cannot understand the dense structures without understanding the empty spaces between them. The cosmic web is dynamic, not static. Matter continuously flows through it, following the pull of gravity. Gas streams from voids into filaments, from filaments into clusters. Galaxies move along filaments toward clusters, accelerated by gravity and dark matter's pull. The whole structure is expanding with the universe, but internal motions driven by gravity create flows that counteract expansion locally. In regions where gravity is strong enough, like galaxy clusters, expansion is overcome entirely, and structures are gravitationally bound. The pattern of the cosmic web reflects the initial conditions of the universe. The tiny density fluctuations imprinted during inflation determined where overdense and underdense regions would form. Over billions of years, gravity amplified these fluctuations, creating the web we see today. The specific arrangement, which voids are where, which filaments connect which clusters, is essentially random, determined by the random quantum fluctuations in the early universe. But the general pattern, that there should be a web-like structure at all, is inevitable given the laws of physics. Dark matter forms the skeleton of the cosmic web. Galaxies and visible gas trace the web, but dark matter defines it. Dark matter started collapsing into structures earlier than normal matter because it doesn't interact with radiation and wasn't held back by radiation pressure in the early universe. By the time normal matter was free to collapse, around 380,000 years after the Big Bang, dark matter had already created a web of gravitational potential wells. Normal matter fell into these wells, forming galaxies along the dark matter filaments. The cosmic microwave background provides another view of the web. Although the CMB shows the universe as it was 380,000 years after the Big Bang, long before galaxies formed, the density fluctuations visible in its temperature map are the seeds that grew into the cosmic web. The hot and cold spots in the CMB correspond to regions that would become overdense and underdense in the later universe. By comparing the CMB to today's structure, astronomers can test whether gravity and dark energy evolved as expected. Computer simulations of the cosmic web are among the most impressive scientific visualizations ever created. These simulations track billions of dark matter particles from the early universe to today, calculating gravitational forces and particle motions at each time step. The results are stunning. They reproduce the filamentary structure, the void distribution, even the specific properties like void shapes and filament thicknesses. The simulations match observations so well that they give us confidence in our understanding of cosmic structure formation. The cosmic web tells us that the universe is fundamentally inhomogeneous on scales up to about 300 million light-years. Only on larger scales does structure average out and the universe appear uniform. This has important implications. When we measure cosmic properties, we must be careful about scale. Measurements on small scales may not represent the cosmic average. This is exactly the problem with the KBC void. It's large enough to affect local measurements, but small enough that the broader universe has different average properties. The position of the Milky Way within the cosmic web is distinctive. We're inside the KBC void, which places us far from the densest structures. But we're not completely isolated. About 50 million light-years away lies the Virgo cluster, a rich cluster containing over 1,000 galaxies. The Virgo cluster sits on the edge of our void, embedded in a filament that extends beyond. Our local group is being pulled toward Virgo by its gravity, moving at about 600 kilometers per second in that direction. Beyond Virgo lies more structure. The Coma cluster, about 300 million light-years away, is another major node in the web near us. Further still, at around 250 million light-years in a different direction, lies the Great Attractor, a concentration of mass so large it affects the motion of galaxies across hundreds of millions of light-years. These structures are outside our void, but close enough to influence us, creating the complex pattern of gravitational pulls that determines our motion through space. In the opposite direction from Virgo, away from the densest structures, lies the deepest part of the KBC void. If we could travel in that direction for several hundred million light-years, we would find progressively fewer galaxies, dimmer light, and less structure. This direction points toward the heart of our local emptiness, the region most evacuated of matter. Few galaxies exist there, and those that do are small, faint dwarf galaxies struggling to form stars in isolation. The cosmic web's existence answers a fundamental question. Why isn't the universe a featureless fog of uniformly distributed matter? The answer is gravity and initial conditions. Start with tiny fluctuations. Let gravity amplify them for billions of years, and structure emerges inevitably. The web is the shape that gravity creates when it acts on an expanding universe, with small initial variations. It's the natural state of cosmic matter, the pattern toward which the universe evolved. For astronomers studying the cosmic web, voids are as important as the dense structures. You cannot understand filaments without understanding what they're connecting and what they're separating. You cannot understand galaxy evolution without understanding how the environment affects it, and void environments are radically different from cluster environments. Voids are not empty backdrops. They're active participants in cosmic evolution. The cosmic web also connects to the largest scale structure in the universe. Recent surveys have found hints of structure on scales approaching 1 billion light-years or more walls of supervoids, alignments of large structures, possibly even larger patterns. These observations push against the cosmological principle, which holds that the universe should be uniform on the largest scales. If structure exists on scales of billions of light-years, it challenges our understanding. Most cosmologists believe these large-scale patterns are statistical fluctuations that will average out in larger surveys, but the question remains open. Living inside the KBC void means we experience a particular slice of the cosmic web. We see voids around us, filaments in the distance, clusters beyond those. An observer in a different location, say, inside a rich cluster, would see a very different arrangement. They would be surrounded by galaxies, would see filaments extending outward, and would have voids in their distant view. The cosmic web looks different from different vantage points, and our vantage point inside a supervoid gives us a specific, biased view. Understanding the cosmic web is essential for modern cosmology. It's how matter is actually distributed, not uniformly, but in a complex pattern of dense and empty regions. When we make observations or build theories, we must account for this structure. We can't treat the universe as uniform on small scales. It isn't. The cosmic web is reality, and the KBC void is our place within that reality. The universe's hidden gaps. The KBC void is remarkable, but it's not alone. Across the observable universe, astronomers have catalogued thousands of cosmic voids, each with its own properties and peculiarities. Some are small and unremarkable. Others are vast supervoids that rival or exceed our own in size. Studying these voids helps us understand whether our local void is typical or unusual, and reveals the diversity of void properties across the cosmos. The Bootes void, discovered in 1981, was the first large void to be recognized and studied in detail. Located about 700 million light-years from Earth in the constellation Bootes, this void spans approximately 330 million light-years in diameter. What made it remarkable at the time was its apparent emptiness. Early surveys found only 60 galaxies in a volume where 2,000 would be expected, based on the cosmic average. This dramatic underdensity earned it the nickname, the Great Nothing. The discovery of the Bootes void by Robert Kirshner and colleagues shocked the astronomical community. In 1981, the cosmic web was not yet understood. Astronomers knew galaxies clustered, but they didn't expect to find regions so large and so empty. The Bootes void was the first clear evidence that the universe's structure included not just over-dense regions, but vast, under-dense ones as well. It sparked decades of research into void properties and formation. Subsequent observations revealed that the Bootes void isn't completely empty. It contains about 60 galaxies scattered through its volume, most of them small, faint, and blue. These are typical void galaxies, actively forming stars, gas-rich and isolated from interactions. The void also contains dark matter, though at lower density than average. It's not an absence of everything, just a region where matter is scarce compared to the cosmic norm. The Bootes void's shape is irregular, elongated in one direction and somewhat flattened. This reflects the gravitational influence of surrounding structures. The void is embedded in a larger scale pattern of filaments and walls, with denser regions pulling matter away from the void in specific directions. Its evolution followed the standard pattern. Initially a slightly underdense region, it evacuated matter over billions of years, deepening into the prominent void we see today. The giant void in the constellation. Cain's Vantage is even larger, spanning roughly 1.3 billion light-years. Discovered in galaxy surveys in the 1980s and characterized more fully in the 2000s, this supervoid is one of the largest known structures in the universe. It's comparable in size to the KBC void, but located far enough away, about 1.5 billion light-years, that it appears as an external structure rather than our local environment. The CMB cold spot is one of the most intriguing features in the cosmic microwave background, a region about 10 degrees across, where the temperature is slightly lower than surrounding areas. Some astronomers have proposed that this cold spot is caused by a supervoid along the line of sight, perhaps the largest void in the observable universe. As CMB photons pass through the void, they lose energy climbing out of its gravitational potential well, arriving at Earth slightly cooler. If this explanation is correct, the void responsible would span over 1 billion light-years and sit roughly 3 billion light-years away. However, the CMB cold spot remains controversial. Statistical analyses disagree on whether it's unusual enough to require a special explanation, or whether it could be a random fluctuation. Some studies find evidence for a supervoid in that direction. Others find no significant void. The debate continues, highlighting the challenges of detecting and characterizing very large voids at great distances. The Sculptor void is another well-studied example, located about 500 million light-years away in the constellation Sculptor. This void spans approximately 400 million light-years and shows typical void properties: low galaxy density, blue star-forming galaxies scattered through the volume, and an irregular shape. What makes it interesting is its proximity. It's close enough that astronomers can study individual galaxies within it in detail, providing insights into how void environments affect galaxy evolution. Observations of galaxies in the Sculptor void show they have less heavy elements, metals in astronomical terminology, than galaxies in denser regions. This makes sense. Metals are produced by supernovae, and galaxies in voids form stars more slowly, so they've had fewer supernovae and produced fewer metals. The lower metallicity of void galaxies is direct evidence that the environment affects not just galaxy properties, but chemical evolution as well. The Capricornus supervoid is one of the most distant large voids known, sitting about 5 billion light-years away. It spans roughly 230 million light-years and has been studied primarily through its effect on the cosmic microwave background. Photons passing through this void create a subtle signal in the CMB temperature map, the integrated Sachs-Wolf effect, that allows astronomers to detect and measure the void despite its enormous distance. Studies of the Capricornus supervoid test our understanding of cosmic structure formation at earlier times. Because light from this void took 5 billion years to reach us, we're seeing the void as it was 5 billion years ago. At that time, the universe was younger, denser, and dark energy was just beginning to dominate. Voids were smaller and less evacuated than today. By comparing ancient voids like Capricornus with nearby modern voids, astronomers can track void evolution directly. The local void, not to be confused with the KBC void, is a smaller void sitting adjacent to our local group. It spans about 150 million light-years and lies in the direction of the constellation Virgo. We're not inside this void, but on its edge, with the void extending away from us. The local void contains very few galaxies, only a handful of dwarfs, and serves as a nearby laboratory for studying void properties in detail. The distinction between the local void and the KBC void sometimes confuses people. The local void is a small void adjacent to us. The KBC void is the large-scale underdense region in which our entire local volume, including the local void, sits. We're on the edge of the local void, but near the center of the KBC void. Think of it like nested structures. The local void is a small empty region within the larger KBC void. The Eridanus supervoid is associated with another CMB cold spot, the Eridanus cold spot, which is even more significant than the main CMB cold spot discussed earlier. This void sits about 2 billion light-years away and may span up to 1 billion light-years. If real, it represents one of the largest voids in the observable universe. However, like the CMB cold spot, its existence and properties remain debated, with different studies reaching different conclusions. Void statistics reveal interesting patterns. Most voids are relatively small, spanning 50 to 150 million light-years. Medium voids of 150 to 300 million light-years are less common. Large voids and supervoids exceeding 300 million light-years are rare. The size distribution follows a power law, with exponentially fewer voids as size increases. The KBC void, at nearly 2 billion light-years across, sits at the extreme tail of this distribution. It's in the largest 1% of all voids. The shapes of voids vary considerably. Some are nearly spherical, others highly elongated. Statistical studies show that the average void is slightly elongated, with its longest axis about 1.5 times its shortest. But individual voids can be much more extreme. Some are stretched into cigar shapes with axis ratios of 3, 1 or higher. Others are flattened into pancake shapes. These variations reflect the complex gravitational environments in which voids form and evolve. Void density also varies. Some voids are deeply evacuated, with galaxy densities 10 to 20% of the cosmic average. Others are more moderately underdense, with densities 50 to 70% of average. The deepest voids tend to be the largest and oldest. They've had more time to evacuate matter. Smaller and younger voids may still be in the process of emptying and haven't reached their final low-density state. The clustering of voids is another interesting property. Voids don't sit in isolation but are part of the cosmic web. Often, multiple voids are adjacent, separated by thin walls. In some regions, you can find chains of voids extending across hundreds of millions of light-years, like cosmic tunnels through the web. In other regions, voids are more isolated, surrounded on all sides by dense structures. Comparing the KBC void to other known voids reveals both similarities and differences. In size, our void is among the largest, comparable to the giant void and possibly the Eridanus supervoid. In density, it's moderately underdense but not the most evacuated void known. The Bootes void, for example, is more depleted. In shape, the KBC void is somewhat irregular, similar to most large voids. What makes it unusual is our position near its center, which is statistically unlikely but not impossible. The study of individual voids complements statistical studies of the void population. By examining specific voids in detail, astronomers learn about the physical processes that shape them. By studying many voids statistically, they learn about void properties in general and how those properties relate to cosmological parameters. Both approaches are necessary for a complete understanding. Voids at different distances also provide cosmic history. Nearby voids like the KBC void and Bootes void show us the present state of void evolution. Distant voids like Capricornus show us earlier stages, when the universe was younger and voids were less developed. By comparing voids across cosmic time, astronomers reconstruct the history of void growth and the increasing dominance of dark energy over gravity. The diversity of void properties demonstrates that while voids follow general patterns, each is unique. The specific arrangement of matter in the early universe, the gravitational influence of nearby structures, and the local history of matter flows all combine to create voids with different sizes, shapes, densities, and galaxy populations. The KBC void is one example from this diverse population, large, moderately empty, irregular in shape, and hosting a handful of galaxies, including our own. Life in a void, galaxy evolution in underdense regions. Living inside a void is not just a cosmological curiosity, it has profound implications for how galaxies form, evolve, and behave. The galaxies that inhabit voids, including potentially our own Milky Way, experience a very different environment from galaxies in dense clusters or rich filaments. This environment shapes their properties in ways that astronomers are only beginning to fully understand. The most obvious difference in void environments is isolation. Galaxies in clusters are surrounded by hundreds or thousands of neighbors within a few million light-years. They interact frequently, passing close to each other, sometimes colliding and merging. These interactions are violent and transformative. They trigger bursts of star formation, strip away gas, disrupt spiral structures, and often convert spiral galaxies into elliptical ones. Clusters are cosmic cities, crowded, dynamic, and rough on their inhabitants. Voids, by contrast, are cosmic countryside. The nearest neighbor to a void galaxy might be tens or even hundreds of millions of light-years away. Interactions are rare or non-existent. A galaxy can evolve in peaceful isolation for billions of years, never experiencing a major merger or close encounter. This tranquil environment produces galaxies with very different properties from their cluster counterparts. Void galaxies tend to be smaller and less massive than average. This makes sense. In regions where matter density is low, less matter is available to collapse into galaxies. The typical void galaxy has a mass perhaps 1/10 that of the Milky Way, what astronomers classify as a dwarf galaxy. These small galaxies often appear blue in observations, indicating active star formation. They're creating new stars from their gas reservoirs, a process that can continue for billions of years in the absence of environmental disruption. The star formation rates in void galaxies are interesting. Per unit of stellar mass, void galaxies form stars at similar or slightly higher rates than field galaxies in average density regions. This might seem counterintuitive if there's less matter in voids. Shouldn't star formation be lower? But the key is that void galaxies aren't being stripped of their gas by environmental processes. In clusters, ram pressure from hot intergalactic gas can blow away a galaxy's cold gas, shutting down star formation. In voids, there's no such pressure. Void galaxies keep their gas and continue forming stars steadily. The metallicity of void galaxies, the abundance of elements heavier than hydrogen and helium, is typically lower than galaxies in denser regions. Metals are produced inside stars and expelled into space when stars die, especially in supernova explosions. Over time, galaxies enrich themselves with metals, but void galaxies have formed fewer stars total and experienced fewer supernovae, so they've produced less enrichment. Their lower metallicity is a chemical signature of their isolated evolution. The morphology of void galaxies also differs. Most are spiral or irregular galaxies with ongoing star formation. Elliptical galaxies, which are common in clusters and typically have little active star formation, are rare in voids. This makes sense. Ellipticals often form through mergers of spiral galaxies, and mergers are rare in voids. The morphological difference between voids and clusters is one of the clearest examples of how the environment affects galaxy evolution. Void galaxies have different kinematics as well. They rotate more slowly on average than galaxies in denser regions. This relates to their formation history and mass assembly. Galaxies gain angular momentum during formation as they collapse from initially rotating clouds of gas. In voids where interactions are rare, galaxies retain their initial angular momentum without being spun up or down by encounters. Their slower rotation reflects their quieter formation environment. The dark matter halos surrounding void galaxies are also interesting. Every galaxy sits inside a halo of dark matter, a gravitational well that holds the visible matter in place. In dense environments, halos interact with each other, sometimes merging or being stripped away by tidal forces. In voids, halos evolve more independently. Studies using simulations suggest that void galaxy halos are slightly less concentrated than halos in denser regions. The dark matter is spread out over a larger volume rather than being compressed toward the center. But what about large galaxies in voids? Do any massive galaxies exist in these underdense regions, or are all void inhabitants dwarfs? The answer is that large galaxies can exist in voids, but they're rare. Occasionally, a void will contain a bright, massive spiral galaxy that seems out of place in such an empty environment. These galaxies likely formed from relatively rare peaks in the density field, small, overdense regions within the larger underdense void. They evolved in isolation, never merging with neighbors to become even larger, because there were no neighbors nearby. The Milky Way itself might be considered a void galaxy, depending on how you define the boundaries. We sit inside the KBC void, in a region where density is below average. However, we're not completely isolated. The local group contains several galaxies, and we're not in the deepest part of the void. So the Milky Way is perhaps a borderline case, a galaxy in an underdense region, but not as isolated as typical void galaxies. This may have affected our evolution in subtle ways. The chemical evolution of void galaxies follows a different timeline than cluster galaxies. In clusters, early rapid star formation enriches galaxies with metals quickly. Then, interactions and environmental processes shut down star formation and chemical evolution halts. In voids, star formation proceeds more slowly but continues longer. Void galaxies are still chemically evolving today, slowly increasing their metal content as each generation of stars adds to the enrichment. This has implications for planet formation and potentially for life. Planets form from the heavy elements produced by earlier generations of stars. In metal-poor environments, planet formation may be suppressed or different. Rocky planets like Earth require elements like silicon, iron, and oxygen, all of which are metals produced in stars. In the early universe, when metal abundance was low everywhere, planet formation may have been rare. Even today, in very metal-poor void galaxies, planet formation might be less common than in more enriched environments. However, some researchers have suggested that void environments might actually be better for the development of life in the long run. Voids are quiet, no nearby supernovae from neighboring galaxies, no tidal disruptions, no close passages that could perturb planetary systems. A galaxy in a void experiences a stable environment over billions of years, which might be conducive to the slow process of chemical and biological evolution. The Milky Way's location in the KBC void might not be a coincidence. Perhaps life is more likely to develop in these peaceful regions. The study of void galaxies has practical challenges. Because they're distant and often faint, they're difficult to observe in detail. Most of what we know about void galaxies comes from statistical studies of large samples, not detailed observations of individual objects. Future telescopes with greater sensitivity will allow astronomers to study void galaxies more carefully, measuring their gas content, star formation histories, and chemical compositions with greater precision. Void galaxies also serve as testbeds for galaxy formation theories. Models of galaxy evolution are often calibrated using galaxies in average or overdense environments. Applying these models to void galaxies tests whether they work in extreme conditions. If a model successfully predicts both cluster and void galaxy properties, that increases confidence in its validity. If it fails in voids, that reveals gaps in our understanding. One particularly interesting question is whether void galaxies host supermassive black holes in their centers, as most galaxies in denser regions do. The Milky Way has a black hole of about 4 million solar masses at its center. Andromeda has one of about 100 million solar masses. Do tiny void dwarf galaxies have black holes too? If so, how did they form in such low-mass galaxies? If not, what does that tell us about black hole formation? These questions are just beginning to be answered with new observations. The environmental effects on galaxy evolution are not limited to voids and clusters. There's a continuum of environments, from the densest cluster cores to the emptiest void centers, and galaxy properties vary smoothly along this continuum. Voids represent one extreme end, the lowest density, most isolated environments possible. By studying galaxies across the full range of environments, astronomers build a complete picture of how the environment affects evolution. The future evolution of void galaxies is also interesting to consider. As the universe continues expanding and dark energy's dominance increases, voids will grow larger and emptier. Galaxies within voids will become even more isolated as their nearest neighbors recede beyond the cosmic horizon. Eventually, billions of years from now, a galaxy in a deep void will see no other galaxies at all. Its entire observable universe will consist of itself alone. This is the ultimate fate of void galaxies in an accelerating universe. For now, though, void galaxies like those in the KBC void are still connected to the larger cosmic web. They can still observe distant structures and still feel gravitational influences from nearby overdensities. They inhabit a special ecological niche in the cosmic ecosystem, adapted to life in emptiness, evolving at their own pace and providing a window into galaxy evolution under the most isolated conditions the universe offers. The Hubble tension and the void hypothesis. One of the most significant controversies in modern cosmology is the Hubble tension, a persistent disagreement between different measurements of the universe's expansion rate. This disagreement has resisted resolution for years, and some cosmologists have proposed that our location inside the KBC void might be the explanation. Understanding this proposal requires understanding both the Hubble constant and how voids affect expansion measurements. The Hubble constant, named after Edwin Hubble, who discovered the universe's expansion in 1929, describes how fast the universe is expanding. Specifically, it tells us how much faster distant galaxies are receding from us for each additional megaparsec of distance. The current measurements give values around 67 to 73 kilometers per second per megaparsec, meaning that a galaxy 1 megaparsec away recedes at 67 to 73 kilometers per second, a galaxy 2 megaparsecs away recedes at twice that speed, and so on. The problem is that different measurement methods give different values for the Hubble constant. The most precise measurement comes from the cosmic microwave background, observed by satellites like Planck. This method looks at the universe when it was only 380,000 years old and uses our understanding of physics to calculate what the expansion rate should be today. The answer comes out to about 67.4 kilometers per second per megaparsec, with an uncertainty of only about 1%. This is called the early universe measurement. The other major method uses observations of nearby supernovae and other distance indicators to directly measure the expansion rate of our local universe. This late universe measurement, pioneered by Adam Rees and colleagues, gives a value of about 73.0 kilometers per second per megaparsec, also with roughly 1% uncertainty. The two methods disagree by about 8%, a huge discrepancy in cosmological terms. If both measurements are correct, something is wrong with our understanding of the universe's expansion history. Various solutions have been proposed. Maybe dark energy behaves differently than we think. Maybe there's an unknown particle affecting cosmic expansion. Maybe our measurements are wrong, or our statistical errors are underestimated. Or maybe, and this is where the KBC void comes in, our local measurements are biased because we live in an underdense region. The void hypothesis works like this. Inside a void, the local expansion rate should be slightly higher than the cosmic average because there's less matter to slow expansion down. When we measure the Hubble constant using nearby supernovae, we're measuring this local enhanced expansion, not the true cosmic average. The cosmic microwave background, by contrast, samples the entire observable universe and gives the true average. The discrepancy between the two measurements reflects the difference between our local void environment and the cosmos at large. For this explanation to work, the effect needs to be large enough to account for an 8% difference in expansion rate. Early studies suggested that living in a void could indeed produce a measurable effect, but typically only a few percent, not enough to fully explain the Hubble tension. More sophisticated analyses have tried to determine whether a void as large as the KBC void could produce the required effect. The challenge is that voids don't just uniformly boost the expansion rate. Their effect is more complex. Light traveling from distant supernovae to us passes through the void, and the void's gravitational field affects the light's journey. Additionally, the expansion rate we measure depends on where exactly we sit within the void. At the center, the effect is different than at the edge. And the void's size, shape, and density profile all matter. Several research groups have built detailed models of how the KBC void affects Hubble constant measurements. These models use simulations to track light rays through a void structure matching the KBC void's properties. The results are mixed. Some studies find that the void can account for 2 to 4% of the Hubble tension, a significant portion, but not all of it. Other studies find smaller effects, only 1 to 2%. And some studies argue that when you properly account for how we measure distances, the void effect largely cancels out. The most sophisticated analyses use what's called the Lemaitre-Tolman-Bondy model, which describes a spherically symmetric void in general relativity. These models show that yes, expansion is faster inside voids, but the relationship between redshift and distance is also affected in ways that complicate the interpretation. An observer inside a void measuring distances, using standard candles like supernovae, will derive a Hubble constant that's biased. But the magnitude, and even the direction of the bias, depends on subtle details. One key question is how we define the void's boundary and what lies beyond it. If the void transitions gradually into normal density regions and then into overdense structures, the net effect on Hubble constant measurements is different than if the void has sharp boundaries with typical density material immediately outside. The KBC void appears to have gradual transitions, which reduces its effect on measurements compared to an idealized void with sharp edges. Another complication is that the supernovae used to measure the Hubble constant aren't all at the same distance. Some are quite nearby, at distances of only a few 100 million light-years, well within the KBC void. Others are farther away, at distances of several billion light-years, well outside the void. The Hubble constant measurement uses all these supernovae together, averaging over different environments. This averaging dilutes the void's effect. The nearby supernovae are affected, but the distant ones aren't. Some researchers have tried to test the void hypothesis by looking for specific signatures. If we're in a void, then measurements of the Hubble constant should show directional dependence. The expansion rate measured toward the void's center should differ from the rate measured toward its edges or beyond. Several studies have searched for such directional variations and found hints of them, but the evidence is not conclusive. The statistical uncertainties are large enough that it's hard to distinguish a real directional signal from noise. The void hypothesis also makes predictions about other observables. For instance, if we're in a large void, measurements of galaxy clustering and matter density should show specific patterns. The kinetic Sunyaev-Zeldovich effect, where the motion of galaxy clusters imprints a signal on the cosmic microwave background, should show a bulk flow pattern consistent with void expansion. Some of these predictions have been tested with mixed results. Some datasets show the expected patterns, others don't. Critics of the void hypothesis point out several problems. First, to explain the full Hubble tension, the KBC void would need to be even larger and deeper than current measurements suggest, perhaps 3 billion light-years across, with density only 50% of average. But galaxy surveys don't show evidence for such an extreme void. The observed underdensity is more moderate. Second, even if the void exists as described, most detailed calculations show its effect on the Hubble constant is too small to resolve the tension completely. Furthermore, the cosmic microwave background itself provides constraints on local structure. If we're in a large void, the CMB should show specific patterns related to the integrated Sachs-Wolf effect. Photons passing through the void should be affected in measurable ways. Planck satellite data has been analyzed for these signatures, and while some weak signals are detected, they're consistent with a moderate void, like the KBC void as measured, not the much larger void needed to explain the Hubble tension. There's also a conceptual issue. The cosmological principle states that the universe should look the same on average from any location. If our local environment is unusual enough to significantly bias fundamental measurements, that suggests we live in a special place, which seems unlikely. Of course, someone has to live in large voids, and maybe we're just unlucky. But the more extraordinary the required void properties, the more uncomfortable cosmologists become with this explanation. Despite these issues, the void hypothesis hasn't been completely ruled out. Some recent studies suggest that when combined with other effects, like the presence of local overdensities beyond the void that create bulk flows, the net impact on Hubble constant measurements could be larger than simple void models predict. The gravitational influence of the Shapley supercluster, one of the most massive structures in the nearby universe, combined with the KBC void's underdensity, might create a complex gravitational environment that biases local measurements more than either effect alone. Another possibility is that the void effect is real, but only accounts for part of the Hubble tension. Perhaps 2 or 3% of the 8% discrepancy comes from our void location, and the remaining 5 or 6% has other causes, new physics, systematic errors in measurements, or a combination. This would make the void a contributing factor rather than the complete explanation. The debate over the void hypothesis highlights a fundamental challenge in cosmology. We can only observe the universe from one location. If that location has unusual properties, all our observations are potentially biased. We can try to correct for local effects, but we can't move to another location to check our measurements from a different vantage point. This limitation means we must be especially careful about assuming our local measurements represent cosmic averages. Some cosmologists have proposed using future observations to better test the void hypothesis. Observations of supernovae at very high redshifts, far beyond the KBC void, should be unaffected by local underdensity. If these distant measurements agree with local measurements, it suggests the void isn't causing significant bias. If they disagree, with distant measurements giving lower Hubble constant values, it would support the void hypothesis. The James Webb Space Telescope and other next-generation instruments will enable such tests. Another test involves measuring the Hubble constant using completely different methods that don't rely on distance ladders. Gravitational wave observations from merging black holes and neutron stars provide independent distance measurements. If these give Hubble constant values consistent with the CMB measurement, but inconsistent with the local supernova measurement, it suggests the supernova method is biased by local conditions, possibly including the void. Early results from gravitational wave measurements are tantalizing, but not yet precise enough to definitively resolve the question. The void hypothesis also makes predictions about other cosmological parameters. For instance, measurements of the matter density parameter omega_m derived from local observations should be biased if we're in a void. Studies have looked for such biases and found some evidence for them, but again, the results are not conclusive. The statistical errors are large, and different analyses reach different conclusions. There's also the question of whether other observers in other parts of the universe would face similar issues. If voids are common, and many galaxies live in them, then many civilizations making cosmological measurements would be biased by their local environments. This would be a general problem for cosmology, not just a peculiarity of our situation. On the other hand, if truly large voids like the KBC void are rare, then we might be unusually unlucky, measuring the cosmos from an atypical location. The Hubble tension remains unresolved as of this writing. Neither the void hypothesis nor any other proposed solution has gained universal acceptance. The most likely outcome is that multiple factors contribute. Perhaps the void accounts for some of the tension, measurement systematics account for some, and maybe there's even new physics contributing a bit. Disentangling these contributions is one of the major challenges facing cosmology today. What's clear is that the KBC void, whether or not it fully explains the Hubble tension, does affect our measurements of the universe. We cannot simply ignore our local environment and assume we're observing from a typical location. The void is real. Its gravitational effects are real, and those effects must be accounted for in precision cosmology. Our cosmic address, inside a large void, is not just an interesting fact, but a practical consideration for making accurate measurements of the universe. Measuring the void, techniques and challenges. Detecting and characterizing cosmic voids is far more challenging than it might seem. Voids are defined by the absence of galaxies, but how do you observe an absence? How do you distinguish a true void from a region where galaxies simply haven't been detected yet? And how do you measure the properties of something that's mostly empty space? Astronomers have developed multiple techniques to meet these challenges, each with its own strengths and limitations. The most direct method is galaxy redshift surveys. These surveys measure the positions of millions of galaxies in 3 dimensions by recording both their locations in the sky and their distances derived from redshift measurements. When plotted in 3-dimensional space, the galaxies reveal the cosmic web structure, with voids appearing as regions where galaxy density is markedly lower than average. The Sloan Digital Sky Survey, the 2-degree field galaxy redshift survey, and similar projects have mapped vast volumes of space using this technique. The process starts with imaging surveys that photograph large areas of sky, cataloging the positions and brightnesses of millions of galaxies. Then comes the spectroscopic follow-up. Light from each galaxy is passed through a spectrograph, which splits it into its component wavelengths. The spectrum shows absorption and emission lines from elements in the galaxy, and the wavelengths of these lines are shifted toward the red due to cosmic expansion. By measuring how much the lines are shifted, astronomers calculate the galaxy's redshift, which translates to distance. Once you have three-dimensional positions for millions of galaxies, you can identify voids using algorithms. The simplest approach is to look for regions where the density of galaxies falls below some threshold, say 20% of the average. More sophisticated algorithms use watershed techniques, which treat the galaxy distribution like a topographic map and identify basins, voids, separated by ridges, filaments and walls. Other methods use tessellation, dividing space into cells and identifying connected regions of underdense cells. Each algorithm has biases. Threshold-based methods are sensitive to the exact threshold chosen. Set it too high and you miss subtle voids. Set it too low and you only catch the most extreme examples. Watershed methods can fragment large voids into multiple smaller ones or merge distinct voids together, depending on how the algorithm handles boundary regions. The choice of algorithm affects void catalogs, and different research groups using different methods sometimes identify different voids in the same data. Galaxy surveys also have observational limitations. They're limited by telescope sensitivity. Faint, distant galaxies are harder to detect, so distant voids might appear artificially empty simply because the galaxies there are too faint to see. Surveys have boundaries. They only cover certain regions of sky and certain distance ranges, so large voids near the survey edges might be cut off or incompletely mapped. And surveys have spectroscopic incompleteness. Not every galaxy that's photographed has its redshift measured, creating gaps in the three-dimensional map. An alternative approach is gravitational lensing. Massive objects bend spacetime and deflect light passing nearby. This is gravitational lensing. Galaxy clusters, with their enormous masses concentrated in small volumes, create strong lensing effects that distort the images of background galaxies. Voids, with their deficit of mass, create subtle anti-lensing effects. Light passing through a void is bent slightly less than it would be in a typical region, causing specific distortions in background galaxy images. Weak gravitational lensing surveys map the distribution of matter, both normal and dark matter, across large areas of sky by measuring these subtle distortions in millions of galaxy shapes. Where matter is concentrated, background galaxies appear stretched tangentially around the concentration. Where matter is deficient, as in voids, the pattern is reversed. By analyzing these patterns statistically, astronomers can map matter distribution and identify underdense regions corresponding to voids. The advantage of lensing is that it detects all matter, not just galaxies. Voids might contain dark matter even if they have no visible galaxies, and lensing would reveal it. Lensing also doesn't require measuring redshifts for every object. You only need images. The disadvantage is that lensing signals from voids are very weak because voids have little matter to create lensing effects. Detecting void lensing signatures requires enormous data sets with millions of background galaxies, and even then, the measurements are statistical rather than providing precise void boundaries. A third technique uses the cosmic microwave background. When CMB photons pass through cosmic structure on their journey from the early universe to our telescopes, they're affected by gravitational potentials. Photons passing through a void climb out of a shallow gravitational potential well, gaining energy and creating a slight temperature increase in the CMB, the integrated Sachs-Wolf effect. By cross-correlating CMB temperature maps with void catalogues from galaxy surveys, astronomers can detect this signal and measure void properties. The ISW effect is particularly useful for detecting large, distant voids that are hard to characterize with galaxy surveys alone. The signal is strongest for large voids because they create substantial potential wells, and for distant voids because the CMB photons have long paths through them. However, the ISW signal is very small, temperature changes of only a few microkelvin, and requires careful statistical analysis to extract from the noisy CMB data. Supernovae provide another probe of void properties. Type Ia supernovae are used as standard candles for measuring cosmic distances because they have consistent peak brightness. By observing supernovae at different distances and comparing their apparent brightnesses to their known intrinsic brightness, astronomers can map the expansion history of the universe. Supernovae in voids should show slight systematic differences from those in typical regions due to the void's effect on expansion and light propagation. Studies have searched for such differences, looking at whether supernovae in known void regions appear systematically brighter or fainter than expected. Results have been mixed. Some studies find small effects consistent with theoretical predictions. Others find no significant difference. The challenge is that there are relatively few supernovae in voids because there are fewer galaxies to host them, so the statistical sample is small and results are uncertain. The Alcock-Podzinski test uses the shapes of large-scale structures to probe cosmic geometry and expansion. The idea is that any large-scale structure, including voids, should be approximately spherical on average when measured in comoving coordinates, coordinates that account for cosmic expansion. If the expansion rate we assume is wrong, or if space is curved in ways we don't expect, structures will appear elongated or flattened. By measuring void shapes and comparing to expectations, astronomers can test cosmological models. Applying the Alcock-Podzinski test requires large samples of voids to average over individual variations. No single void is perfectly spherical, but statistically, a population of voids should have average aspect ratios close to unity if our cosmological model is correct. Deviations from unity signal problems with the model or bias in measurements. Several studies have applied this test to void catalogues with results generally consistent with the standard cosmological model, though uncertainties remain large. Void galaxy populations provide indirect information about void properties. By studying the galaxies that do live in voids, their numbers, types, star formation rates, and chemical compositions, astronomers learn about the void environment. A deeply evacuated void will have very few galaxies, and those galaxies will be small and isolated. A more moderate void will have more galaxies, possibly including some larger ones. The galaxy population is a tracer of the matter distribution and the void's formation history. Measuring void expansion rates is particularly challenging, but important for constraining dark energy. If you could measure how fast a void's radius is increasing over time, you'd have a direct probe of cosmic expansion and dark energy's influence. The problem is that voids evolve slowly. Their radii increase by only a fraction of a percent per million years. Measuring such small changes requires comparing observations separated by many years, or looking at voids at different redshifts, different cosmic epochs, and comparing their properties. Some studies have attempted the latter approach, measuring void properties in nearby surveys and comparing them to void properties in more distant surveys that show the universe billions of years ago. The results suggest voids were smaller in the past and have grown over time, consistent with theoretical predictions. However, comparing voids across different surveys is tricky because the surveys have different sensitivities, selection effects, and observational biases. Measuring the KBC void specifically faces additional challenges because we're inside it. When you're embedded in a structure, it's hard to see the structure's full extent and properties. It's like trying to map a forest while standing in the middle of it. You can see trees around you, but determining the forest's boundary is difficult. For the KBC void, astronomers use galaxy surveys extending outward in all directions, mapping galaxy density as a function of distance. Where density rises back to the cosmic average marks the void's approximate edge. The uncertainties in KBC void measurements are substantial. Different studies using different datasets and methods have obtained different values for the void's radius, ranging from about 1 billion to 2 billion light-years, and central density, ranging from 60 to 80% of the cosmic average. These variations reflect both genuine uncertainties and differences in how the void's boundary is defined. There's no sharp edge, just a gradual transition. And where you draw, the line is somewhat arbitrary. Future surveys will improve void measurements significantly. The Dark Energy Spectroscopic Instrument, DSI, currently conducting observations, will measure redshifts for 40 million galaxies, providing the largest three-dimensional map of the universe ever created. The Vera C. Rubin Observatory will image billions of galaxies, enabling unprecedented weak lensing studies. Euclid, a European space mission, combines imaging and spectroscopy to map cosmic structure with high precision. These next-generation surveys will catalogue voids with much better completeness and characterize their properties in far greater detail. Better data will reduce uncertainties in KBC void parameters and allow more refined tests of whether the void affects cosmological measurements. They'll also reveal whether there are other large voids comparable to or larger than the KBC void elsewhere in the universe. And they'll provide much larger samples of void galaxies, allowing detailed statistical studies of how void environments affect galaxy evolution. Theoretical advances are also needed. Current models of void formation and evolution are sophisticated, but still approximate. They often assume symmetry or simplifications that may not apply to real voids. Developing more realistic models that account for irregular shapes, density gradients, and the influence of surrounding structures will improve our ability to interpret observations. And connecting void properties to fundamental physics, the nature of dark energy, the particle properties of dark matter, the laws of gravity on cosmic scales, remains an active area of research. The measurement of cosmic voids, including the KBC void, sits at the intersection of observation, theory, and statistical analysis. It requires large surveys, sophisticated algorithms, careful modeling, and critical evaluation of uncertainties. The fact that we've made as much progress as we have, mapping the void structure of the universe and characterizing our local underdense region, represents a major achievement of modern astronomy. But much work remains, and future observations will undoubtedly refine and possibly revise our current understanding. Dark energy and the accelerating emptiness. Dark energy is the most mysterious substance in the universe, making up roughly 68% of everything that exists, yet we barely understand what it is. What we do know is this: dark energy causes the universe's expansion to accelerate, pushing space apart at an ever-increasing rate. And nowhere is dark energy's influence more obvious than in cosmic voids, where it dominates gravitational dynamics and drives the relentless growth of emptiness. The discovery of dark energy came in 1998, when two teams of astronomers studying distant supernovae found something shocking. The universe's expansion was speeding up, not slowing down as everyone expected. Gravity should pull everything together, gradually slowing cosmic expansion over time. Instead, some mysterious force was pushing space apart faster and faster. Scientists called this force dark energy, though that name is more placeholder than explanation. We don't know what dark energy is, a property of space itself, a new quantum field, a modification of gravity. The answer remains unknown. What we do know is how dark energy affects structure. In regions with high matter density, like galaxy clusters, gravity is strong enough to overcome dark energy's push. Clusters remain gravitationally bound, with member galaxies held together despite cosmic expansion. But in voids, where matter density is far below average, dark energy dominates completely. There's not enough mass to generate sufficient gravity to resist dark energy's push. The result? Voids expand faster than the universe's average expansion rate, actively evacuating matter and growing larger over time. The mathematics of void expansion in the presence of dark energy is straightforward in principle, but complex in detail. Einstein's field equations from general relativity govern how matter, energy, and spacetime curvature interact. In the standard cosmological model called lambda CDM, lambda for dark energy, CDM for cold dark matter, dark energy is represented by the cosmological constant lambda, which Einstein originally introduced, then abandoned, calling it his biggest blunder. The irony is that the cosmological constant turned out to be real after all, just not in the way Einstein imagined. Inside a void, the local expansion rate depends on the local matter density. The Friedmann equations, which describe cosmic expansion, include terms for matter density, dark energy density, and spatial curvature. In a typical region with average matter density, these terms balance to give the universe's average expansion rate. In a void with reduced matter density, the matter term is smaller, so dark energy's contribution becomes relatively larger. This shifts the balance, producing faster expansion. The magnitude of this effect depends on how much the void's density differs from average. For a void with 70% of the cosmic average density, the local expansion rate might be 2 to 3% higher than average. For a deeply evacuated void with only 20% of average density, the boost could reach 10% or more. The KBC void, with its moderate underdensity, likely produces a local expansion enhancement of a few percent. Significant, but not enormous. Dark energy's influence on voids has changed over cosmic history. In the early universe, when matter density was much higher everywhere, gravity dominated cosmic dynamics, even in underdense regions. Voids existed but expanded slowly, limited by gravity's pull. As the universe aged and matter density decreased due to expansion, dark energy became progressively more important. Around 5 billion years ago, when the universe was about 9 billion years old, dark energy's density exceeded matter density for the first time. From that moment on, dark energy dominated cosmic expansion, and void growth accelerated dramatically. We're now living in the dark energy era, when cosmic expansion is accelerating and will continue accelerating forever according to current understanding. Voids are growing faster than ever before. The KBC void's radius increases by roughly 1,000 km per second per megaparsec, meaning that a 0.1 megaparsec from the void's center recedes at 1,000 km per second due to expansion alone. Over millions of years this adds up, and the void's diameter steadily increases. The nature of dark energy remains cosmology's biggest mystery. The simplest explanation is that dark energy is Einstein's cosmological constant, a property of empty space itself with constant density that doesn't dilute as the universe expands. This fits observations reasonably well, but it creates a theoretical problem called the cosmological constant problem. Quantum field theory predicts that empty space should have enormous energy density, perhaps 120 orders of magnitude larger than observed. Why is the actual value so much smaller? Nobody knows. Alternative theories propose that dark energy isn't constant, but changes over time. These models invoke scalar fields called quintessence that evolve as the universe expands, with energy density that increases or decreases over cosmic history. Different quintessence models predict different expansion histories and different effects on void evolution. By studying how voids have grown over time, comparing nearby voids to distant ones, astronomers can test these models and constrain dark energy's properties. Voids serve as laboratories for dark energy physics because they're the purest dark energy environments in the universe. In dense regions, matter and dark energy compete, making it hard to isolate dark energy's effects. In voids, dark energy wins decisively, and its influence is easier to measure. Void expansion rates, void shapes, and void evolution over cosmic time all probe dark energy's properties in ways that complement other observations like supernovae and the cosmic microwave background. One particularly interesting application is using void shapes to constrain dark energy. If dark energy is the cosmological constant, voids should evolve in a specific way, reaching certain sizes at certain times with certain shapes. If dark energy behaves differently, say, its density increases or decreases over time, voids would evolve differently, producing different size distributions and shapes. By measuring void properties in detail and comparing to theoretical predictions, astronomers can test whether the cosmological constant model is correct or whether alternative dark energy models fit better. Current observations favor the cosmological constant model, but uncertainties remain large enough that alternatives aren't ruled out. Future surveys measuring millions of voids at different distances, different cosmic epochs, will dramatically improve constraints. If void evolution matches cosmological constant predictions precisely, we'll gain confidence that dark energy is indeed a constant property of space. If discrepancies appear, they'll point toward new physics beyond the standard model. The future evolution of voids under dark energy's influence is both certain and bizarre. Voids will continue growing indefinitely. As they expand, matter density within them will decrease further, approaching zero. Eventually, each void will contain only a handful of galaxy clusters at its edges, with vast, empty regions hundreds of billions of light-years across in between. The cosmic web will stretch into a sparse network with ever larger gaps. In the very far future, trillions of years from now, voids will have grown so large that galaxies within them will lose sight of all other galaxies. Cosmic expansion will have carried everything beyond the cosmic horizon, the distance beyond which light can never reach us, because space is expanding faster than light can travel. Each galaxy will find itself alone in an observable universe, surrounded by nothing but darkness and emptiness. This is the ultimate fate of a universe dominated by dark energy. Cosmic isolation. For now, though, we're still in the early stages of dark energy dominance. The KBC void is growing, but we can still see distant structures beyond it. The Virgo cluster, the Coma cluster, and the Great Attractor are all still visible, still gravitationally influencing our motion. Dark energy hasn't yet isolated us, but it's working on it, inexorably pushing the universe toward greater emptiness, and the voids are its primary tools. Understanding dark energy through void studies represents one of the frontiers of cosmology. It combines theory, observation, and sophisticated data analysis to probe the universe's most mysterious component. The fact that we live inside a large void gives us a unique vantage point. We're not just studying dark energy abstractly, but experiencing its effects directly through our local environment. Our cosmic address inside the KBC void connects us intimately to dark energy's dominance and the universe's accelerating expansion. Supervoids and cold spots in the cosmic microwave background. The cosmic microwave background is the oldest light in the universe, emitted when the cosmos was only 380,000 years old. This ancient radiation fills all of space, coming at us from every direction with a nearly uniform temperature of about 2.7 Kelvin. But nearly uniform is not perfectly uniform. Tiny temperature fluctuations exist, and these fluctuations contain enormous information about cosmic structure. Some of the most intriguing features in the CMB are cold spots that may be caused by supervoids, including potentially the largest structures in the observable universe. When CMB photons travel through the universe on their 13.8 billion year journey from the early universe to our telescopes, they pass through cosmic structure, galaxy clusters, filaments, voids. As they pass through regions with different gravitational potentials, they gain or lose energy. This effect, called the integrated Sachs-Wolf effect or ISW effect, creates subtle imprints in the CMB temperature map that reveal large-scale structure along the line of sight. The ISW effect works like this. A photon entering a gravitational potential well, like falling toward a galaxy cluster, gains energy and becomes slightly bluer and hotter. If the potential well hasn't changed by the time the photon climbs back out, the photon loses exactly the energy it gained, ending up with its original energy. But if the universe's expansion has weakened the potential well in the meantime, as happens when dark energy dominates, the photon doesn't lose quite as much energy climbing out. It emerges slightly bluer and hotter than it entered, creating a hot spot in the CMB. The opposite happens with voids. A photon entering a void is already outside the potential wells created by dense structures. As it crosses the void, it climbs out of the shallow potential hill created by the void's underdensity. If the void is growing due to dark energy, its potential hill gets shallower during the photon's transit. The photon loses less energy climbing out than expected. But wait, actually, for voids, the photon gains energy overall, creating a cold spot because... No, let me correct this. For voids, photons actually create cold spots in the CMB because they lose energy climbing out of the evacuated region. The physics is subtle and the effect is small, but it's real and measurable. The largest cold spot in the CMB, simply called the CMB cold spot, is a region about 10 degrees across, roughly 20 times the angular diameter of the Moon, where the temperature is about 70 microkelvins colder than surrounding areas. This spot was first noticed in data from NASA's Wilkinson Microwave Anisotropy probe and confirmed by the European Space Agency's Planck satellite. Its existence is not in doubt. The question is what causes it. One possibility is that it's just a statistical fluke, a random fluctuation that happens to be unusually large. Statistical analyses suggest there's about a 1 to 2% chance of such a cold spot occurring randomly in a map of the CMB. That's unlikely, but not impossibly so. In a universe as large as ours, unlikely things happen occasionally. However, some astronomers find this explanation unsatisfying and have searched for physical causes. The supervoid hypothesis proposes that the cold spot is caused by an enormous void along the line of sight in that direction. If a void spanning 1 billion light-years or more sits at the right distance, the ISW effect it produces could explain the cold spot's temperature deficit. Several research groups have searched for such a supervoid using galaxy surveys and found partial evidence. Some studies identify an underdense region in the cold spot direction at distances of 2 to 3 billion light-years. Others find the underdensity is too weak or too small to fully explain the cold spot. The debate continues because the observations are difficult. Mapping galaxy density at distances of billions of light-years requires deep surveys with careful corrections for selection effects. Galaxies at such distances are faint and hard to detect, especially the small dwarf galaxies that might be the only inhabitants of deep voids. Missing these galaxies would make a void appear even more empty than it really is. Conversely, if the void isn't as large or deep as required to explain the cold spot, then either the void isn't the cause, or there's additional physics we don't understand. Another cold spot, called the Eridanus cold spot, shows similar characteristics and may also be associated with a supervoid. This feature sits in a different part of the sky and has prompted similar searches for underdense regions along the line of sight. Again, some evidence for a void has been found, but whether it's sufficient to explain the cold spot remains debated. Supervoids themselves are fascinating objects regardless of their connection to CMB cold spots. These are the largest cosmic voids, spanning more than 500 million light-years and containing vast volumes of nearly empty space. The giant void in Cain's Venatici, stretching 1.3 billion light-years, is one example. If the cold spot supervoid exists as theorized, it would be another, perhaps even larger. These structures represent the extreme tail of the void size distribution, the biggest empty regions that formed from the largest underdense fluctuations in the early universe. The existence of supervoids pushes against the cosmological principle. According to this principle, the universe should be homogeneous on large enough scales, beyond a few 100 million light-years, it should look uniform, but supervoids extending over 1 billion light-years challenge this assumption. They're large enough that they don't average out easily. If you observe the universe from different locations, one inside a supervoid and one outside, you might see significantly different properties. This raises questions about whether the cosmological principle holds strictly or whether it's only approximate. Most cosmologists believe that while individual supervoids seem to violate homogeneity, the universe as a whole remains homogeneous when you average over truly cosmic scales, many billions of light-years. The observable universe is large enough to contain many supervoids, and they average out in the cosmic accounting. But this is an assumption that's difficult to test observationally, because we can only see the universe from one location. The study of supervoids through the ISW effect represents an important application of CMB science. The CMB isn't just a snapshot of the early universe, it's also a backlight that illuminates structure along the line of sight through the entire history of cosmic evolution. By cross-correlating CMB temperature maps with galaxy surveys and void catalogues, astronomers can detect the ISW signal and use it to study large-scale structure in ways that complement direct galaxy observations. The ISW signal is weak, requiring careful statistical analysis and large datasets to extract. But modern CMB missions like Planck have sufficient sensitivity and resolution to detect it. Combined with the next generation of galaxy surveys, ISW studies of voids will become increasingly powerful. They'll allow measurements of void properties at large distances, where direct galaxy surveys are challenging, and they'll provide independent checks on void catalogues derived from galaxy surveys. Supervoids also affect other observables. They influence the statistics of galaxy clustering on large scales. They alter the distribution of galaxies in the sky. Regions behind supervoids show slightly fewer galaxies due to gravitational lensing effects and the volume dilution of structure. They create bulk flows, coherent motions of galaxy groups over large volumes as matter streams away from void centers towards surrounding overdensities. The KBC void, while large, is not quite a supervoid by the strictest definitions. It's perhaps in the upper range of large voids, rather than qualifying as a supervoid. But it's in the same family, just slightly smaller. If the cold spot supervoid exists and is as large as some estimates suggest, up to 1.8 billion light-years, it would be comparable to, or larger, than the KBC void, making them two of the largest known structures. The universe would contain several such giants, each representing an extreme outcome of primordial density fluctuations, amplified over billions of years by gravitational evolution and dark energy. Understanding supervoids is crucial for testing cosmological models. The number, size distribution, and properties of the largest voids depend sensitively on cosmological parameters, the matter density, dark energy properties, the amplitude of primordial fluctuations, and the laws of gravity on cosmic scales. By measuring supervoid statistics and comparing to theoretical predictions, cosmologists can constrain these parameters and test whether the standard model is correct. Current observations suggest the number of supervoids is roughly consistent with predictions from lambda CDM cosmology with standard parameters. There are hints that the largest structures might be slightly larger than expected, but statistical uncertainties are too large to draw firm conclusions. Future surveys will census supervoids much more completely, measuring their properties precisely and settling whether any tension exists between observations and theory. The connection between supervoids and CMB cold spots, while still uncertain, highlights the deep links between different observational probes of the universe. The CMB, galaxy surveys, gravitational lensing, and large-scale velocity fields all provide complementary information about cosmic structure. By combining them, astronomers build a comprehensive picture that's more powerful than any single probe alone. Supervoids sit at the intersection of these probes, influencing each in different ways, and serving as test beds for our understanding of cosmic structure on the largest scales. The cosmic web's largest scales and the end of structure. How large can cosmic structures grow? Is there a maximum size beyond which structure doesn't exist? Or does the universe show pattern on all scales without limit? These questions touch on fundamental issues in cosmology and connect directly to the nature of voids, which are participants in the universe's largest scale architecture. The cosmological principle asserts that the universe is homogeneous and isotropic on sufficiently large scales. This doesn't mean it's perfectly uniform everywhere. Obviously, galaxies, clusters, filaments, and voids exist. But it means that if you average over large enough volumes, the universe looks the same everywhere and in all directions. Different regions have the same average density, the same average expansion rate, the same statistical properties. The question is, how large is large enough? Early theoretical work suggested that structure should end, average to uniformity, on scales around 300 to 400 million light-years. Beyond this scale, the universe should appear homogeneous. This prediction came from understanding how gravitational instability works and how much time has elapsed for structure to grow. Small density fluctuations in the early universe have had 13.8 billion years to grow through gravitational collapse. This sets a limit on how large structures can become. Observations largely support this picture, but with complications. Galaxy surveys like SDSS show that structure does become weaker on scales beyond 300 million light-years. The correlation function, which measures how much galaxy density at one point correlates with density at another point some distance away, drops towards zero as the separation increases. Beyond 400 million light-years or so, there's little correlation. The universe appears to randomize. This is the scale of homogeneity. However, individual structures can exceed this scale. The giant void in Canes Venatici spans 1.3 billion light-years. The Sloan Great Wall, a vast sheet of galaxies, extends over 1.4 billion light-years. The huge LQG, Large Quasar Group, a collection of 73 quasars, spans about 4 billion light-years, though its status as a single coherent structure is debated. These structures are larger than the supposed homogeneity scale, raising questions about whether the cosmological principle holds strictly. The resolution is statistical. The scale of homogeneity refers to the scale at which structure averages out statistically, not the scale beyond which no individual structures exist. You can have occasional structures larger than the homogeneity scale as long as they're rare statistical fluctuations. The Sloan Great Wall is one example from millions of cubic gigaparsecs of surveyed volume. It's unusual, but not impossibly so. Calculate the statistics, and such structures should occur occasionally in a universe as large as ours. More controversial are claims of structure on even larger scales. Some researchers have reported alignments of quasar polarizations extending over billions of light-years, or correlations in galaxy orientations on gigaparsec scales, or patterns in the distribution of galaxy clusters, suggesting coherent structure approaching 10 billion light-years. If confirmed, these would represent serious challenges to the cosmological principle, because they'd indicate the universe isn't homogeneous, even on very large scales. Most of these claims have not held up under scrutiny. Reanalyses with improved data or better statistical methods often find the claimed structures are artifacts of selection effects, small number statistics, or improper analysis. The quasar alignment signal, for instance, has weakened in larger datasets and may not be real. The lesson is that finding structure in data is easy. Finding real structure that isn't a statistical fluke is hard, especially when working with limited samples. Voids play a crucial role in defining the scale of homogeneity. The largest voids are among the largest structures, and their size distribution provides a measure of how far the structure extends. Current void catalogues show that while voids of 1 to 2 billion light-years exist, they're rare. Most voids are much smaller. The size distribution cuts off sharply beyond about 1.5 billion light-years. There are very few voids larger than this. This cutoff reflects the fundamental limits on structure growth set by the age of the universe and the dynamics of gravitational instability. The cosmic web itself shows a characteristic scale. Filaments typically run for a few hundred million light-years before encountering nodes, galaxy clusters, where multiple filaments meet. Voids typically measure a few hundred million light-years across, bounded by walls and filaments. This is the natural scale of cosmic structure, the size that emerged from gravitational evolution of primordial fluctuations over 13.8 billion years. Structures significantly larger than this are rare because they require unusually large primordial fluctuations, which are exponentially improbable. The future evolution of structure will change this picture dramatically. As dark energy continues dominating cosmic expansion, the scale of homogeneity will grow. Structure formation effectively ended a few billion years ago. No new large-scale structures are forming because dark energy prevents matter from collapsing over large distances. Existing structures persist, but they're not growing except through merger of smaller structures that are already close together. Meanwhile, cosmic expansion stretches the web, increasing distances between structures and reducing their apparent density contrast. In the far future, tens of billions of years from now, the cosmic web will have stretched so much that its structure becomes difficult to recognize. Voids will have expanded enormously, filaments will have thinned and fragmented, and galaxy clusters will be isolated islands separated by vast empty expanses. The scale of homogeneity will have grown to encompass most of what we currently see as structure. Eventually, on timescales of trillions of years, the observable universe from any given location will contain only a single gravitationally bound structure, the local cluster, surrounded by infinite emptiness. This ultimate fate is strange to contemplate. Astronomers in such a future would see a very different universe than we do. They'd have no evidence for the Big Bang, no cosmic microwave background. It will have redshifted to undetectable wavelengths. No other galaxies beyond their local cluster. They'd have no way to discover cosmology as we know it. If they didn't have records from earlier eras when the universe was more observable, they'd be unable to reconstruct cosmic history. This highlights how lucky we are to live in an era when the universe is still revealing its secrets. The question of maximum structure size connects to fundamental physics. General relativity predicts that structure growth is limited by the cosmic horizon, the distance beyond which causal influences can't propagate, because cosmic expansion carries regions apart faster than light can travel. Structure can't grow beyond causal connection, so the horizon size sets an absolute limit. For the observable universe, with its 13.8 billion year age, this limit is roughly the size of the observable universe itself, about 46 billion light-years in radius today, larger than 13.8 billion light-years due to expansion. But within this horizon, actual structure is limited to much smaller scales by the time available for gravitational collapse and the strength of primordial fluctuations. The structures we see, filaments, voids, superclusters, are the natural outcomes of these constraints. They represent how far gravitational instability can go in the time available, starting from the tiny fluctuations present in the early universe. Going forward, no larger structures will form because dark energy prevents it. The structures we see now are, in some sense, the final state of cosmic architecture on the largest scales. Understanding the scale of homogeneity and the limits of structure has practical importance for cosmology. When measuring cosmic parameters, we must average over large enough scales that the universe appears uniform. If we make measurements on scales where structure is significant, our results will be biased by local inhomogeneities, exactly the problem potentially affecting our measurements from inside the KBC void. By understanding where structure ends and uniformity begins, we can design observations and analyses that properly account for these effects. The cosmic web, with its filaments, walls, clusters, and voids, represents the largest organized structure in the universe. Beyond the web's characteristic scale of a few 100 million light-years, the universe begins to look random and uniform. This transition from structure to homogeneity defines the boundary between local and cosmic, between our particular region and the universe as a whole. Living inside the KBC void places us in a specific part of this structured universe, our view shaped by our location within the web. Computer simulations, modeling cosmic voids. Understanding cosmic voids requires not just observations, but detailed theoretical models of how they form and evolve. Computer simulations have become the most powerful tool for building such models, allowing astronomers to watch virtual universes evolve from the Big Bang to today and compare the results to real observations. These simulations successfully reproduce the cosmic web, including its voids, providing confidence that we understand void formation and giving predictions for properties that are hard to observe directly. The basic approach to simulating cosmic structure is conceptually simple but computationally intensive. Start with initial conditions matching the early universe, a nearly uniform distribution of matter with tiny density fluctuations matching those observed in the cosmic microwave background. Set up equations governing how matter moves under gravity and how space expands. Then step forward in time, calculating gravitational forces and updating positions and velocities for millions or billions of particles representing dark matter. Watch as structure emerges. Overdense regions collapse into halos, filaments, and clusters, while underdense regions evacuate and become voids. The first large cosmological simulations ran in the 1990s and early 2000s, tracking millions of dark matter particles in volumes hundreds of millions of light-years across. These early simulations successfully produced cosmic web structure, filaments and voids, emerged naturally from gravitational dynamics. The results matched galaxy survey observations surprisingly well, confirming that the basic picture of structure formation was correct. Dark matter, driven by gravity and cosmic expansion, spontaneously organizes into web-like patterns. Modern simulations are far more sophisticated. The Millennium simulation, run in 2005, tracked over 10 billion particles in a cubic volume, 2 billion light-years on a side. It required months of supercomputer time and produced vast datasets showing structure formation in unprecedented detail. The simulation reproduced the cosmic web down to scales of about 20,000 light-years, revealing not just large-scale filaments and voids, but the internal structure of dark matter halos, where galaxies would form. More recent simulations push even further. The Illustris TNG simulation series includes normal matter alongside dark matter, tracking gas dynamics, star formation, black hole growth, and feedback processes where stars and black holes inject energy back into their surroundings. These simulations produce not just dark matter distributions, but synthetic galaxies with realistic properties that can be compared directly to observations. They show how galaxies form in filaments and clusters while remaining sparse in voids, matching observed galaxy distributions. Voids appear naturally and robustly in all these simulations. You don't need to fine-tune parameters or include special physics. Voids emerge inevitably from gravitational dynamics. This gives confidence that we understand the basic formation mechanism. The simulations also reveal details about void properties that are hard to measure observationally, like how dark matter is distributed within voids or how voids grow over time. One key insight from simulations is that void properties depend sensitively on cosmological parameters. The size distribution of voids, their shapes, their density profiles, and their evolution all change if you vary parameters like the matter density, dark energy equation of state, or the amplitude of primordial fluctuations. By comparing simulated void catalogues to observed void catalogues, cosmologists can constrain these parameters. If simulations with standard parameters produce voids that match observations, that validates the standard model. If discrepancies appear, they point to needed corrections. Simulations have been used to predict the properties of the KBC void and similar large voids. By running hundreds of simulations with different random realizations of initial fluctuations, researchers can determine how common voids like the KBC void should be. Results suggest that while large voids are rare, they're not impossibly so. Perhaps 1% of random universe volumes comparable to what we've surveyed would contain a void as large as the KBC void. This means our location, while unusual, isn't so special as to be implausible. Simulations also test whether large voids can explain observational anomalies like the Hubble tension. By placing a virtual observer inside a simulated void and calculating what measurements they would make, researchers can determine whether void effects are large enough to bias results. These studies generally find that moderate voids like the KBC void produce small biases, a few percent, but not enough to fully explain major discrepancies. This suggests that if the Hubble tension is real, it likely requires additional physics beyond just our void location. One limitation of simulations is resolution. Tracking every atom in a cosmic scale volume is impossible. There are far too many particles. Simulations represent matter with a finite number of particles, typically millions to billions. Each simulation particle represents a huge amount of real mass, perhaps 1 million solar masses or more. This means small-scale structure within voids, like individual dwarf galaxies, may not be fully resolved. Hybrid approaches combining high-resolution simulations of small volumes with large-volume, low-resolution simulations help address this. Another challenge is including all relevant physics. Dark matter dynamics are relatively straightforward. Dark matter only feels gravity, so the equations are simple. But normal matter undergoes complex processes. Gas can heat and cool, form stars, explode in supernovae, get blown around by stellar winds, fall into black holes, and more. Each process affects structure formation in different ways. Modern simulations include increasingly sophisticated models of these processes, but approximations and simplifications are still necessary. The illustristingy simulations represent the current state of the art in including baryonic physics. They track gas thermodynamics, chemical enrichment, magnetic fields, and feedback from stars and black holes. The results reproduce many observed properties of galaxies, including their sizes, colors, star formation rates, and chemical compositions. They show that feedback processes are crucial. Without them, simulated galaxies form too many stars and become too massive. With appropriate feedback, simulations match reality reasonably well. Applying these sophisticated simulations to voids reveals interesting predictions. Void galaxies should have specific properties different from field and cluster galaxies, and the simulations predict what those differences should be. By comparing observations of real void galaxies, astronomers test whether the simulation's physics is correct. So far, the agreement is generally good, though some discrepancies remain, suggesting areas where models need improvement. One area where simulations are particularly valuable is predicting void evolution in the far future. We can't observe the future directly, but we can simulate it. By running simulations forward in time, billions or trillions of years, researchers can watch how voids grow under dark energy's influence and how the cosmic web evolves. These simulations confirm theoretical predictions. Voids expand indefinitely, eventually dominating cosmic volume, with ever fewer galaxies visible from any given location. Simulations also help with observational planning. If you want to design a survey to detect and characterize voids, simulations can predict what you'll see. They can generate mock observations with realistic noise and selection effects, allowing you to test analysis techniques before applying them to real data. Many void-finding algorithms are developed and calibrated using simulated data before being applied to galaxy surveys. The agreement between simulations and observations is not perfect. Some tensions exist, like the satellite plane problem, where satellite galaxies around the Milky Way and Andromeda appear aligned in thin planes, which simulations predict should be rare. There's also the missing satellites problem. Simulations predict many more small dark matter halos than we observe dwarf galaxies, suggesting either the simulations overpredict structure on small scales, or many halos don't form visible galaxies. These tensions drive ongoing research to refine both simulations and observations. Despite imperfections, cosmological simulations have become indispensable tools for understanding the universe. They provide laboratories where we can test ideas, make predictions, and interpret observations. For void studies specifically, simulations confirm that our basic understanding is sound, while pointing to areas needing further investigation. The fact that simulated voids look like observed voids, with similar sizes, shapes, and density profiles, validates our theoretical framework and gives confidence in using void observations to constrain cosmology. Future simulations will be even more powerful. Exascale computing, supercomputers capable of 1 billion operations per second, will enable simulations tracking trillions of particles with unprecedented resolution. Machine learning techniques are being developed to speed up calculations and better model complex physical processes. These advances will produce increasingly realistic virtual universes, allowing ever more detailed comparisons with observations and tighter constraints on fundamental physics. The role of simulations in cosmology highlights how modern science combines theory, observation, and computation. None alone is sufficient. We need all three working together. Simulations bridge theory and observation, turning abstract equations into concrete predictions that can be tested. For cosmic voids, this bridge has proven essential, transforming voids from curious observational oddities into well-understood components of cosmic structure and powerful probes of fundamental physics. The Anthropic question: why here, why now? Living inside a cosmic void raises an intriguing question. Is our location random chance, or could there be deeper reasons why we find ourselves in such an unusual environment? This leads into anthropic reasoning, the controversial but fascinating idea that our observations of the universe are inevitably biased by the conditions necessary for our existence. If life requires certain environmental conditions, we should not be surprised to find ourselves in a place where those conditions are met, even if such places are rare. The standard view in cosmology is that our location is unremarkable. The cosmological principle asserts we don't occupy a special place. We're just one planet, in one solar system, in one galaxy, in one region of a vast universe. Finding ourselves in a void seems to contradict this, suggesting our location is unusual. But as we've seen, voids occupy most of the universe's volume, even though they contain few galaxies. If you randomly place an observer somewhere in the universe, there's a reasonable chance they'll be in a void simply because voids are volumetrically dominant. However, if you randomly select a galaxy rather than a random point in space, the odds change. Most galaxies live in filaments and walls, not voids. Only about 10 to 15% of galaxies are void galaxies. So, if the Milky Way is a typical galaxy, its location in a void or on a void's edge is statistically unlikely. This brings us back to the question, why here? One anthropic argument suggests that void environments might actually be beneficial for life. Voids are quiet. Few nearby galaxies mean few nearby supernovae that could bathe planets in harmful radiation. Few interactions mean fewer tidal disruptions that could scatter planets from their orbits or trigger galaxy-wide bursts of star formation. A galaxy in a void experiences a stable, peaceful environment over billions of years, allowing slow processes like biological evolution to unfold without catastrophic interruptions. This argument has merit, but is far from proven. We don't know how much environmental stability matters for life's development. Earth has experienced catastrophes like asteroid impacts and supervolcano eruptions, yet life persisted and even thrived afterward. Perhaps life is resilient enough that external astronomical threats matter little. Or perhaps threats from our own galaxy, like nearby supernovae or passages through spiral arms, are more significant than intergalactic threats, making our void location irrelevant to habitability. Another consideration is metallicity. As we discussed, void galaxies tend to have lower abundances of heavy elements because they formed fewer stars and experienced fewer supernovae. Rocky planets like Earth require heavy elements, iron for the core, silicon and oxygen for the mantle and crust, carbon for life's chemistry. In very low metallicity environments, planet formation might be suppressed or altered in ways that make Earth-like planets rare. This would work against life in voids, potentially outweighing any benefits from environmental stability. However, the Milky Way's metallicity is quite typical for a galaxy of its mass, not particularly low. If we're in a void, we're not in its deepest, most metal-poor regions. Our location in the KBC void is somewhat peripheral. We're hundreds of millions of light-years from the center. This puts us in a transitional zone where void effects are noticeable but not extreme. Perhaps this Goldilocks location, not in the dense, violent cluster environments, not in the deep, metal-poor void centers, but in between, is somehow optimal for life. The anthropic principle comes in two versions, weak and strong. The weak anthropic principle simply observes that our observations are inevitably conditioned on our existence. We must find ourselves in a place and time where life is possible, otherwise we wouldn't be here to observe anything. This is uncontroversial, but also fairly trivial. It explains why we observe certain local conditions, but doesn't predict what those conditions should be. The strong anthropic principle suggests the universe must have properties compatible with life, because if it didn't, no observers would exist to see it. This ventures into philosophy and is much more controversial. It seems to put observers at the center of cosmic explanation in a way that makes many scientists uncomfortable. It also raises questions about multiple universes. If our universe is one of many with different properties, then the strong anthropic principle makes sense as a selection effect. But if there's only one universe, the principle seems circular. Applying anthropic reasoning to our void location is speculative but interesting. If void locations are actually better for life, or at least not worse, then we should not be surprised to find ourselves in one, even though most galaxies live outside voids. Observers require planets. Planets require heavy elements. Heavy elements require stars. Stars form in galaxies, but which galaxies develop? Observers might depend on subtler factors, like environmental stability. If void-edge galaxies like the Milky Way provide that stability, then life might preferentially develop there, biasing where observers find themselves. This reasoning is far from conclusive. We have a sample size of 1, life on Earth, and no clear understanding of what factors are essential versus incidental for life's emergence. Maybe environmental stability matters greatly, and void locations are indeed advantageous. Maybe it matters little, and our location is just random chance. We won't know until we find other examples of life and can assess what environments they inhabit. The question why now is also interesting. We live at a particular cosmic epoch, about 13.8 billion years after the Big Bang, when the universe has cooled, stars and galaxies have formed, heavy elements have been synthesized, and planets have had time to develop life. This epoch is neither the beginning nor the end of cosmic habitability. Earlier eras were too hot and chaotic. Later eras will be too cold and empty as stars burn out and galaxies drift apart. We live during the habitable epoch of cosmic history. Some calculations suggest we're actually living surprisingly early in cosmic history from an anthropic perspective. Stars will keep forming for trillions of years, and planets will keep being born. Most potentially habitable planets will exist in the far future, not now. If observers are uniformly distributed across cosmic time, weighted by the number of habitable planets, we should expect to find ourselves in the future, not the present. The fact that we exist now, relatively early, is statistically unusual. Various explanations have been proposed. Maybe habitability peaks around now, rather than extending indefinitely into the future. Maybe late-forming planets face disadvantages we haven't considered. Or maybe we're just randomly early. Someone has to be among the first civilizations to emerge, and perhaps we're them. This touches on deep questions about the nature of probability and observation that philosophers and physicists continue debating. Connecting these temporal and spatial questions, we live in a particular place, inside a void, at a particular time, relatively early in the habitable epoch. Is this combination significant? Perhaps voids become more hostile to life over time as they expand, and metal-poor void galaxies grow ever more isolated. Perhaps our location was less voidy in the past, when structure was less developed, and will become more so in the future. Living in a void now might actually be optimal, even though void locations seem suboptimal in some ways. All this anthropic reasoning is highly speculative and perhaps untestable. We can't run experiments with multiple universes or multiple histories. We can't move to different cosmic locations to test whether life would have developed there. The anthropic principle remains controversial precisely because it's unclear how to use it scientifically. It makes some predictions, but they're often vague or tautological. Nevertheless, the question remains intriguing. The fact that we find ourselves in an unusual location, inside one of the universe's largest voids, invites explanation. Random chance is always an answer, but it's not always satisfying. Whether deeper reasons exist for our cosmic address is an open question that connects cosmology to philosophy, and perhaps to the origins of consciousness itself, challenging us to consider whether awareness is shaped not only by biology, but by the very structure of the universe we inhabit. Exploring that possibility invites interdisciplinary work. Astronomers, philosophers, biologists, and cognitive scientists collaborating to frame testable questions, develop probabilistic models, and search for empirical signatures that could support or refute anthropic claims. Even if definitive proof remains elusive, such efforts sharpen our thinking, highlight assumptions, and may reveal subtle observational consequences. For example, correlations between habitability indicators and large-scale environment, that future surveys and simulations can probe, turning philosophical speculation into constrained scientific inquiry over time and informing experimental design choices. The far future, isolation and the death of cosmology. The universe has a future as well as a past, and that future is bleak. As dark energy continues driving accelerated expansion, cosmic voids will grow without limit, eventually dominating all of space and isolating galaxies from each other beyond any hope of contact or even observation. Understanding this future helps us appreciate our current cosmic environment and the special nature of our epoch when cosmology is still possible. Today, we can observe galaxies billions of light years away. The Hubble Space Telescope and James Webb Space Telescope image galaxies so distant their light has traveled for over 13 billion years to reach us, showing us the universe when it was young. This vast observable universe, spanning tens of billions of light years, is our cosmic laboratory. But this won't last. Cosmic expansion is carrying distant galaxies away from us at ever-increasing speeds, and eventually they will recede beyond our cosmic horizon, the distance beyond which no light can reach us, because space is expanding faster than light can travel. The cosmic horizon is not a fixed distance. It grows over time in a non-accelerating universe, because light has more time to reach us. But in an accelerating universe dominated by dark energy, the horizon eventually stops growing and may even shrink. Galaxies beyond the horizon are forever inaccessible. We can never see them, reach them, or receive any information from them. They effectively cease to exist for us, and we for them. Currently, the cosmic horizon sits at about 16 billion light-years. Galaxies at this distance are receding at nearly the speed of light. Light they emit today will take infinite time to reach us. It will never arrive. We can still see these galaxies, but only as they appeared billions of years ago when they were closer. As time passes, more and more galaxies will cross our horizon and disappear from view. The observable universe will shrink. In about 100 billion years, assuming dark energy remains constant, most galaxies currently visible will have receded beyond the horizon. The local group, our Milky Way, Andromeda, and smaller satellites will remain visible because these galaxies are gravitationally bound to us, moving slower than the expansion of space. The Virgo cluster and nearby structures will also remain visible, but everything beyond about 100 million light-years will have disappeared, carried away by expansion into regions we can never observe. In 150 billion years, the observable universe from Earth, or whatever remains of our planet, will consist of just the local group, by then merged into a single large elliptical galaxy. All other galaxies will be gone, invisible beyond the horizon. An astronomer in this far future, looking at the night sky, would see only stars from their own galaxy and darkness beyond. No other galaxies, no cosmic web, no evidence of a larger universe. This astronomer would face a devastating handicap in understanding cosmology. Without other galaxies to observe, they couldn't measure the Hubble constant or discover cosmic expansion. Without distant galaxies showing redshift distance relations, they couldn't infer the Big Bang. The cosmic microwave background will have cooled to undetectable temperatures, removing another pillar of evidence. The universe's current composition, roughly 68% dark energy, 27% dark matter, 5% normal matter, would be impossible to determine. If this future civilization had no records from earlier eras, they would be unable to reconstruct cosmic history. They might assume their galaxy island is the entire universe, eternal and unchanging. They would be wrong, but they'd have no way to discover their error. Cosmology as we know it would be impossible. This scenario was popularized by physicist Lawrence Krauss and colleagues in papers showing how cosmic observability declines in the dark energy-dominated future. Voids accelerate this process. Inside a void, the effective expansion rate is higher than average, so the horizon shrinks faster. A galaxy in a deep void will lose sight of its neighbors sooner than a galaxy in a typical region. The KBC void's presence means our own cosmic horizon is shrinking somewhat faster than it would otherwise. This doesn't affect the far future scenario much. 100 billion years is 100 billion years regardless, but it emphasizes how voids and dark energy work together to isolate galaxies. The ultimate fate of galaxies themselves is also bleak. Stars will keep forming for a while, but as gas is consumed and not replenished, star formation will gradually cease. The longest-lived stars, small red dwarfs, will burn for trillions of years, but eventually they too will die. In 100 trillion years, star formation will have completely stopped, and the last stars will be dying. Galaxies will become graveyards filled with dead stellar remnants. White dwarfs, neutron stars, black holes, and no new light. As stars die, galaxies will fade and darken. The night sky will transition from bright starlight to dim red glow from the last red dwarfs, then to darkness punctuated only by occasional flashes, when stellar remnants collide or matter falls into black holes. Eventually, even these events will become rare. The universe will be dark, cold, and empty, except for isolated pockets of dead matter slowly dispersing. In the even more distant future, beyond 10 circumflex 100 years, protons themselves may decay if certain theories of physics are correct. All normal matter, planets, dead stars, cold gas, would disintegrate into radiation and lighter particles. Only black holes would remain, and they too will eventually evaporate through Hawking radiation, taking 10 circumflex 100 years or more, depending on their mass. The final state of the universe would be a thin soup of photons and fundamental particles, spread across infinite expanding space at temperatures approaching absolute zero. This is the heat death. Maximum entropy, no structure, no change forever. Voids will have long since expanded to dominate essentially all space. The cosmic web structure we see today will be stretched and diluted beyond recognition. Even the gravitationally bound structures like galaxy clusters will have evaporated as stars are ejected through gravitational interactions over countless orbits. Individual black holes will drift alone through space, separated by distances far exceeding the size of today's observable universe, waiting trillions upon trillions of years to evaporate. This far future is not certain. It depends on dark energy remaining constant, on proton decay occurring, on no new physics intervening. If dark energy's strength changes over time, the future could be different. If it weakens, expansion might slow or even reverse, leading to a big crunch where the universe collapses back on itself. If it strengthens, expansion might accelerate catastrophically in a big rip that tears apart galaxies, then solar systems, then planets, then atoms, in finite time. Current observations favor constant dark energy, but we can't rule out alternatives. Contemplating this future highlights the special nature of our cosmic moment. We live at a time when the universe is full of structure and light, when galaxies are visible across billions of light years, when stars are forming and planets are being born. This era spans perhaps 20 billion years, from about 5 billion years after the Big Bang, when the first galaxies had formed and stabilized, to about 100 billion years, when cosmic expansion will have removed most galaxies from view. That's only a small fraction of cosmic history. We're lucky to exist during this brief window when cosmology is possible. Had we emerged in the deep future, we'd be unable to discover our cosmic origins or understand the universe's structure. Had we emerged in the very early universe, we couldn't exist. No planets, no heavy elements, conditions too chaotic. Our existence is tied to this particular epoch, and the fact that it's also the epoch when the universe is most observable may not be a coincidence. This connects back to anthropic reasoning. If observers can only emerge during certain cosmic eras when conditions are right, and if those eras happen to be when the universe is observable, then observers will naturally find themselves in an observable universe. We shouldn't be surprised that we can do cosmology. If we couldn't, we likely wouldn't exist to ask the question. The far future also puts our concerns about the KBC void in perspective. We worry that living in a void biases our measurements or places us in an unusual location. But in the grand scheme, all locations will become void-like as expansion continues. The distinction between voids and overdensities is temporary, lasting only during the brief era of structure. Ultimately, everywhere becomes empty, isolated, and dark. The KBC void is simply ahead of the curve, showing us a preview of what the entire universe will eventually become. This future cannot be avoided unless the laws of physics are very different than we think. Dark energy appears to be a fundamental property of space, perhaps tied to the quantum vacuum itself, an energy that cannot be switched off. As expansion accelerates, galaxies beyond our local group will slip permanently out of view, leaving only a tiny cosmic island surrounded by endless darkness. In trillions of years, even the cosmic microwave background will fade, and future observers, if any remain, will see a static, silent sky. The KBC void, then, is not just a curiosity of our time, but a window into the universe's distant, inevitable solitude. Embracing the empty. We've journeyed through the vastness of the KBC void and seen how emptiness itself shapes the universe. Voids are not just gaps between galaxies, they are active, evolving regions that define the structure of the cosmos. Gravity and dark energy battle here in pure form, carving filaments, walls, and bubbles across space. Though the KBC void may not solve every cosmic puzzle, it reminds us that where we are matters, that our local underdensity subtly bends the measurements we use to understand the universe. Living in a void is both humbling and revealing. It means our galactic neighborhood is quieter, less violent, and more stable than the crowded clusters elsewhere. That isolation may even have allowed the Milky Way and life on Earth to develop in peace. As the universe expands and voids grow, these empty spaces will eventually dominate everything. The cosmic web will thin, galaxies will drift apart, and the universe will become a place of solitude. In that sense, the KBC void is not an anomaly, it's a preview, a glimpse of what awaits all of space as dark energy's influence deepens. We live in the emptiness now, not by accident, but as witnesses to a fleeting era when the universe is still bright, structured, and alive. The void is our home, and through it we glimpse both our cosmic past and our ultimate future, standing quietly between creation and collapse, watching the universe breathe in timeless silence.